Today is our last day. As you already announced, explained our today's schedule. And this might probably be the last time that you see this guy here. So the first thing that I would like to do, because I just remembered some requests. First of all, I'm going to share my email address. So because that was probably not clear to everybody. I would say whenever you have like a dedicated, like well-defined question, I mean, I could explain electron microscopy via the internet and via email. But if you need some, like, let's say, advice or something, let's do this first. Today is our last day. As you already announced, explained our today's schedule. And this might probably be the last time that you see this guy here. So the first thing that I would like to do, because I just remembered some requests. First of all, I'm going to share my email address. So because that was probably not clear to everybody. I would say whenever you have like a dedicated, like well-defined question, I mean, I could explain electron microscopy via the internet and via email. But if you need some, like, let's say, advice or something, let's do this first. You should also be able to find our current website online. Although there's not a lot of information provided yet, as we just started, recently started a few months ago. The second request I would have is that I already talked to some of you. I know that many people of you just recorded some like funny pictures and some like pictures with your cell phones. Just send all of them, or those you would like to share, just to Balaji, probably within the next few hours, because in the morning side he's currently compiling just like a few slides of pictures of our workshop, and you could need one or two more. So whenever you have the chance and internet access, I just would like to ask you just to share the pictures, and we're going to send all those pictures, including our pictures from the TM and SEM sessions and the group picture, to you probably next week. We might not manage that today, so don't worry about. And is there anybody who still needs a feedback form? Because in principle we would for the organizers, we would need to have a feedback form just filled out by every single participant. So, but did everybody fill one? Okay. So today's lecture should be, so this is the last lecture actually, it should be finished until our coffee break. So we should be able in principle to manage that. And I mean, this is somehow somehow an outstanding lecture because I'm not going to talk too much about like imaging and spectroscopic techniques anymore, so you know already almost everything about that. And today I would like to show you how, let's say, how people make use of all that to combine those imaging and spectroscopic techniques. To combine that to carry out like in situ or in operando measurements. What that means, you will see that in a second. I mean, if you're interested in catalysis and you just study a material under vacuum conditions, like nanoparticles on a ceramic substrate, the shape, for instance, of those particles might be totally different. You will see several examples how materials behave during operation. This means that would be in operando experiment, or how materials behave, under certain conditions, like just air compared to high vacuum, for instance. And I mean, most of the microscopes, they are high vacuum instruments, so the material might even look differently compared to regular environment. Although there's not a lot of information provided yet, because we just started, recently started a few months ago. The second request I would have is that I already talked to some of you. I know that many people of you just recorded some like funny pictures and some pictures with your cell phones. Just send all of them, or those you would like to share, just to Balaji. Probably within the next few hours, because in the one inside he's currently compiling just like a few slides of pictures of our workshop, and you could need one or two more. So whenever you have the chance and internet access, I just would like to ask you just to share the pictures, and we're going to send all those pictures, including our pictures from the TM and SEM sessions and the group picture, to you probably next week. We might not manage that today. So don't worry about it. And is there anybody who still needs a feedback form? Because in principle we would, for the organizers, we would need to have a feedback form just filled out by every single participant. So, but did everybody fill one? Okay. So today's lecture should be, so this is the last lecture actually, it should be finished until our coffee break. So we should be able, in principle, to manage that. And I mean, this is somehow an outstanding lecture because I'm not going to talk too much about like imaging and spectroscopic techniques anymore, so you know already almost everything about that. And today I would like to show you how, let's say, how people make use of all that to combine those imaging and spectroscopic techniques. To combine that to carry out like in situ or in operando measurements. What that means, you will see that in a second. I mean, if you're interested in catalysis and you just study a material under vacuum conditions, like nanoparticles on a ceramic substrate, the shape, for instance, of those particles might be totally different. You will see several examples how materials behave during operation. This means that would be in operando experiment, or how materials behave, under certain conditions, like just air compared to high vacuum, for instance. And I mean, most of the microscopes, they are high vacuum instruments, so the material might even look differently compared to regular environment. Is it better? Not really. Is it better? Not really. Better, isn't it? My country is just the level. The level. So let's see. I mean, this term in situ, or like in operando, this it comes from it's Latin, and the translation just means on the spot. I mean, this is like site specific, I would say. But in principle, what we are interested in is to observe any dynamic, like a reaction, a phase transformation, any behavior of the material in a certain, let's say, environment or under certain conditions which are more appropriate, I would say, because we use many materials not just at room temperature and like, let's say, in high vacuum, which we have somehow available in our electron microscope, isn't it? So we want to heat samples, we want to cool samples, we want to stress them in any way to observe how the material behaves or how decomposition occurs or any kind of change occurs, to understand the material's behavior and degradation phenomena and the functionality of the material in a far better way than by just recording static images under high vacuum conditions, okay? And I mean, it's all about, there's a saying which means seeing is believing, and I mean, there's a certain truth in that, because as you will see, there are many examples how you are able to understand what's going on if you conduct such an in situ experiment. So in situ means that you apply a certain stimulus to your sample, and but let's first come back to our introductory slide. I'm going to, after a short introduction into this in situ topic, I'm going to very briefly remind you of like some sample preparation aspects, and we're going to go through somehow the most, I would say, the most like dominant techniques in that field. One is mechanical testing of metals, ceramics, composites, heating, cooling, environmental microscopy, meaning we are able to work under certain gas environments up to very high pressures nowadays. And I'm going to go to, I will address electrical testing. So let me first show you one example. So there are many videos, as you will see, incorporated here. So this is a mechanical testing, just often, this is an indentation experiment, just of an alloy with a diamond indenter. There's some parameters provided, and I mean, you see that plastic deformation just happens on a very localized scale, and I mean, this is somehow how you observe directly. This is what in situ principle means. So in this particular case, this is mechanical testing, this is some deformation, it's an in situ experiment, and you record data, images, or spectroscopic data while any kind of reaction or any change happens. And finally use all that data to come up with a certain model of, let's say, what's going on. And I mean, there's a vast variety of in situ experiments, as you can imagine. I mean, on the one hand side, people are highly interested in, let me just jump to this slide here. Sorry, just look here, because I'm going to jump back in a second. I mean, you know, people are interested. I wanted to show this here first. I didn't shift it. I mean, most of you are interested in any kind, you know, of these material science topics, isn't it? You might be interested in corrosion of alloys. You might be interested in catalysis. People are interested in like oxidation or reduction of any kind of material. Or the structure formation. Structure formation, for instance, could mean the growth of nanoparticles and the formation of nanoparticles with a certain shape. People might be interested in diffusion. You know, I mean, there's a vast variety of questions, isn't it? So, I mean, here we have 50 people, and everybody, I suppose, works in a different field. And so this is just an aspect. I mean, this is about temperature measurements and heating experiments. But in principle, we have all this in mind. You know, on the one hand side, we have the static experiments available. You know about all these capabilities of a regular transmission electron microscope. And now we want to combine that, because I mean, for catalysis, for instance, you don't want to work under high vacuum conditions because the material is totally like different. You might want to work in gas environments, or you might even want to work in a liquid environment, in a transmission electron microscope, or in a scanning electron microscope. You might want to raise the temperature. Temperature which is commonly available, the temperature range starts at liquid nitrogen temperature, or even at liquid helium temperature. For like superconducting experiments, people are interested in phase transformations, or in properties of semiconductors, light emission out of semiconductor material, so you have to quench, you have to reduce the temperature. On the other hand, you might want to do any kind of phase transformation in ceramic material, you might want to go up to very high temperatures. So this is, for instance, the temperature range that is covered. And you can imagine almost any experiment, you just need some, suitable equipment. And I mean, this is just the shape and the kinds of materials people are interested in. I mean, you can have like just 2D materials, nanoparticles, this is already 3D somehow. You might want to extract fibula melee, or you might want to prepare any kind of other TM sample from bulk. So I mean, this is all that I mean you can easily imagine. So let me come back.
How you can work in the different type of environment, because the matrix of part of the electron depends on the vacuum.
Yes, I'm going to address that, but this is just a very brief summary. He was just asking about how to work in an environment, because we have a set mean-free path, to our sample, and I will show you that there are specialized or dedicated sample holders, for instance, available, which just apply this local environment to our TM sample, and it's strongly localized. And you can either do that with a membrane holder, where you confine your gas environment, or you confine your liquid in between two very thin membranes. And I'm going to show you just very few examples. I mean, for some of those experiments, let me just comment on that. I mean, there is commercial TM sample holders, or even dedicated microscopes available. And I mean, for instance, if you have a dedicated environmental transmission electron microscope, I mean, this would be quite expensive. Even such a TM sample holder already costs like 300,000 or so. But for many of those experiments that I will show you, you can also come up with a prototype. Like if you want to do some in situ mechanical testing, for instance, there are many people who just manufacture, let's say, such testing devices, even for a TM, just by themselves. So because there are no commercial products available, so you can do both. I mean, development of techniques, development of sample holders, and of such whatever any kind of testing device. If you want to bias, for instance, your material, you want to run the current through while you observe the material. I mean, you just need somehow the equipment, and people do that by themselves, just having like a workshop available. And so, I mean, there are different ways how to conduct in situ experiments. It's just, this is somehow just to advertise, and I know that it might be challenging for you to conduct such experiments simply due to the fact that there might probably not be the equipment available. But I would like to inform you just that this is state of the art. Many people do that all over the world. And I mean, in worst case, you would just need, let's say, a collaboration with another institute or other experts. You just have to get in touch with those. As I showed you, I mean, there's as you know, a very broad range of materials classes people are interested in. There are many questions. These are just a few examples of something about, let's say, the chemical behavior, like optical questions. And this is just very, very selective. What is of interest today is this so-called stimulus. We apply any stimulus to change or to modify a material, which is somehow related, I would say, to the application. I mean, it doesn't make sense to use very small nanoparticles and heat goes up to 1,000 degrees, as long as they are not intended to be operated under those conditions, So you have to design your experiment in respect to your material science question that you would like to address. I mean, this is quite clear, I would say. And this is just an overview about what I'm going to present you today. So one part will be about mechanical testing in the scanning and the transmission electron microscope. To conduct such experiments, you can easily understand that in an SEM, you already saw that, you have far more space available, isn't it? Far more space available to design such a testing device, for instance, for mechanical testing, because I mean, it's of this size, probably in a transmission electron microscope, you're highly limited because your pole piece gap is so small. I mean, for some of the microscopes, we have a pole piece gap just below 5 millimeters, so 5 mm. Electrical testing, this just means that you conduct like a 2-port or a 4-port measurement, like you come in the on a macroscopic scale. You want to do that on a very localized scale. And I mean, for that, you can either just apply photolithography or electron lithography to generate any kind of structure, electrodes, and you protect those electrodes, or you can make use of those nanomanipulators in a scanning electron microscope, for instance. And here's an example. I will show that later, where we use a very specialized tool that will bias materials in a transmission electron microscope. This is such a heating stage here, so people heat quite a lot, I would say. This is an example of recrystallization in the microscope, in the scanning electron microscope. And you already saw this example of this plating and the generation of lithium tubes, meaning this is a more operando experiment where we run a battery within the transmission electron microscope to investigate it, to study like the oxidation behavior of pure lithium metal. So this is just an overview. And let me remind you of the fact that whenever you have to think about how to prepare your sample and how to access the sample with your whatever kind of probe or you want to contact that. I would like to remind you that whenever you use FIP preparation for many applications and for many of these in situ studies, you apply FIP milling to generate any kind of structure. From your bulk material, you should be aware of the fact that you change your material, at least the surfaces of your sample, by this ion impact, okay? And you have to keep that in mind that like even metals or ceramics can strongly be modified. And this is just one example how the mechanical behavior of a metal changes by FIP milling, okay? So these are some pillars, which are, this is one pillar which is generated just by this gallium ion milling. This is already plastically deformed, so there was some stress applied from the top. This is a common pillar test. The glide planes here are an optimized angle of roughly 45 degrees or so. And here you can directly see how the sample behaves. So this is just the stress strain curve of the material. This is somehow, let's say, the bulk or the like undamaged material. And you can see these stresses exceed the observed stresses in this particular, let's say, experiment or in this application here by far, you know. So there is a clear difference just due to the fact that those samples here were prepared using a focused ion. So, and I mean, you have to be aware of that fact that in this particular case, you form this whatever shell layer around that might enhance the strength of the material, that might lead to reduction. On the other hand, if you conduct experiments like in a gas environment, you have to, for instance, you have to be aware of the fact that your electron beam already ionizes your gas or your liquid. So like pH in the liquid might change simply due to your electron beam irradiation. So I mean, you have your electron beam that might change your environment. Here, you might modify your sample, and so this is what you always have to keep in mind, that for such an in situ experiment, you have to deal with those artifacts. And so you have to overcome those artifacts. This, for instance, is the cross-section of such a metal pillar in the transmission electron microscope. And here you see a very high density of dislocations simply due to the preparation using the ion mill, this ion milling procedure. And after mechanical testing, I mean, this is a very small structure. After mechanical testing, all those dislocations are gone because you have a huge surface area available, and they just moved out to the outer surfaces and it just disappeared. So this is somehow, this is probably the material how it would have been. This is just some artifacts generated by the focused ion beam. In principle, you don't want to have that, so this is what I mentioned. You somehow have to consider all those effects. But nonetheless, people conduct in situ experiments. There are many publications, and it's a very hot topic because people want to correlate, like let's say, the structure, the chemistry of a material on the one hand side, and like the functionality or some degradation of the material on the other. And you might do that ex situ, just to like anneal samples in the furnace and just test in the electron microscope over certain periods of time, or you can do that like during heating experiment within the microscope. This is some, for instance, some mechanical testing device. In this particular case, this is just one of these nanomanipulators, like one of these miniaturized robot arms. And in this particular case, here is like a diamond indenter mounted to that. The sample, it faces this indenter here. And what they make use of, this is just a spring table. These are spring tables, so you mount your sample on one side of this spring here. You know the spring constant, and just by measuring, let's say, this, the relative shift value, and then you can directly correlate it to a force. You don't necessarily need a force measurement device here to come up with a nanomechanical or like such a testing experiment. Because I mean, to realize a force measurement here that might be quite demanding, to make use of such, let's call it a simple spring table where you know the spring constant, this is much easier. But if you want to go down in scale, people use MEMS devices. I mean, there's a vast variety of MEMS devices available for mechanical testing, for electrical testing, for heating. Because I mean, those are small, those can be easily put into a TM sample holder, in a dedicated TM sample holder, to conduct any kind of like measurement. And here, for instance, you measure, let's say, the strain or the shift, for instance, by a capacitance as you apply a certain load. And so there are many examples and devices. So let me just show you one example why this might be of interest. So this is a transition, a phase transition in just silicon. This is just silicon pillars that are prepared. On the left-hand side, this is at room temperature, and all of you know that the silicon wafer behaves like it's brittle. This is what happens here. On the left-hand side, you just apply stress. It's elastically deformed at some point because you have some shear stress. It just chips off. Here on the right-hand side, you see plastic deformation of the silicon wafer. There's some slip occurring here. It's hardly visible. And so, I mean, this is a totally different behavior, isn't it? At room temperature, at high temperature, because of some phase, like some transition within the material, or this plasticity and this ductile behavior. And I mean, this is what people are interested in. For metals, for instance, people are if you do a stretch test because you want to drill holes. You want to see, you directly want to observe the behavior, how the material, like let's say, flakes off, how it comes off, and how these tiny pieces are formed if you want to have like a machinable material. This is a test, just a scratch test in the scanning electron microscope. And I mean, you can do all those tests on various scales. Like this is on the micrometer, far micrometer scale. Here you can go down to the like 10, 20, 50 nanometer scale. This is another example of mechanical testing in a scanning electron microscope, because people are also interested in mechanical behavior of nanoparticles, for instance. So you want to do like some indentation on individual nanoparticles. This is a testing device where you have an indenter. This is a piezo-driven indenter here. The device was developed at Erlangen University. There's a huge group working on nanoparticulate materials, and they wanted to come up with such a testing device to conduct like indentation and like mechanical testing of nanoparticles. They also make use of a spring table here, but they have a load cell installed to that. You mount your sample here with, let's say, your nanoparticles just dispersed, and you apply just a certain load to those nanoparticles in that part. And this was self-made by the group. Let me just show you. So the whole system was developed. This is a video which you don't have in your printout. So this is like an advertisement what they prepared this video. And this is our substrate here. This is our diamond indenter. As you can see, these are all the nanoparticles. This particular project is about the plasticity of glass particles. So this is silica. This is your indenter. The size of these particles is of the order of a few hundred nanometers already. You see this slightly, let's say, brittle behavior. And depending on the density of these particular particles, they are synthesized by a wet chemical route, and they exhibit a certain porosity. So this is quite brittle, the other one was different particle. And I mean, this is, you can just test not only a single particle, by this you can do statistics, you can indent, let's say, 10,000 particles, that just takes you 1 day, and you can come up even with the low displacement curve by that, because you know that. So let's see. I mean, this term in situ, or like in operando, this it comes from it's Latin, and the translation just means on the spot. I mean, this is like site specific, I would say, but in principle, what we are interested in is to observe any dynamic, like a reaction, a phase transformation, any behavior of a material in a certain, let's say, environment or under certain conditions, which are more appropriate, I would say, because we use many materials not just at room temperature and like, let's say, in high vacuum, which we have somehow available in our electron microscope, isn't it? So we want to heat samples, we want to cool samples, we want to stress them in any way, to observe how the material behaves or how decomposition occurs or any kind of change occurs, to understand the material's behavior and degradation phenomena and the functionality of the material in a far better way than by just recording static images under high vacuum conditions, okay? And I mean, it's all about, there's a saying which means seeing is believing, and I mean, there's a certain truth in that, because as you will see, there are many examples how you are able to understand what's going on if you conduct such an in situ experiment. So in situ means that you apply a certain stimulus to your sample, and but let's first come back to our introductory slide. I'm going to, after a short introduction into this in situ topic, I'm going to very briefly remind you of like some sample preparation aspects, and we're going to go through somehow the most, I would say, the most like dominant techniques in that field. One is mechanical testing of metals, ceramics, composites, heating, cooling, environmental microscopy, meaning we are able to work under certain gas environments up to very high pressures nowadays. And I'm going to go to, I will address electrical testing. So let me first show you one example. So there are many videos, as you will see, incorporated here. So this is a mechanical testing, just often, this is an indentation experiment, just of an alloy with a diamond indenter. There's some parameters provided, and I mean, you see that plastic deformation just happens on a very localized scale, and I mean, this is somehow how you observe directly. This is what in situ in principle means. So in this particular case, this is mechanical testing, this is some deformation, it's an in situ experiment, and you record data, images, or spectroscopic data while any kind of reaction or any change happens. And finally use all that data to come up with a certain model of, let's say, what's going on. And I mean, there's a vast variety of in situ experiments, as you can imagine. I mean, on the one hand side, people are highly interested in, let me just jump to this slide here. Sorry, no, just look here, because I'm going to jump back in a second. I mean, you know, people are interested. I wanted to show this here. First, I didn't shift it. I mean, most of you are interested in any kind, you know, of these material science topics, isn't it? You might be interested in corrosion of alloys. You might be interested in catalysis. People are interested in like oxidation or reduction of any kind of material. Or the structure formation. Structure formation, for instance, could mean the growth of nanoparticles and the formation of nanoparticles with a certain shape. People might be interested in diffusion. You know, I mean, there's a vast variety of questions, isn't it? So, I mean, here we have 50 people, and everybody, I suppose, works in a different field. And so this is just an aspect. I mean, this is about temperature measurements and heating experiments. But in principle, we have all this in mind. You know, on the one hand side, we have the static experiments available. You know about all these capabilities of a regular transmission electron microscope. And now we want to combine that, because I mean, for catalysis, for instance, you don't want to work under high vacuum conditions because the material is totally like it's different. You might want to work in gas environments, or you might even want to work in liquid environment. in a transmission electron microscope or in a scanning electron microscope. You might want to raise the temperature. Temperature which is commonly available, the temperature range starts at liquid nitrogen temperature or even at liquid helium temperature. For like superconducting experiments, people are interested in phase transformations or in properties of semiconductors, light emission out of semiconductor material, so you have to quench, you have to reduce the temperature. On the other hand, you might want to do any kind of phase transformation in ceramic material, you might want to go up to very high temperature. So this is, for instance, the temperature range that is covered. And you can imagine almost any experiment, you just need some suitable equipment. And I mean, this is just the shape and the kinds of materials people are interested in. I mean, you can have like just 2D materials, nanoparticles, this is already 3D somehow. You might want to extract fibula melee, or you might want to prepare any kind of other TM sample from bulk. So I mean, this is all that I mean you can easily imagine. So let me come back.
How we can work in the different type of environment, because the main trick of part of this electron returns on the wave.
Yes, I'm going to address that, but this is just a very brief summary. He was just asking about how to work in an environment, because we have a set mean-free path, to our sample, and I will show you that there are specialized or dedicated sample holders, for instance, available, which just apply this local environment to our TM sample, and it's strongly localized. And you can either do that with with a membrane holder where you confine your gas environment, or you confine your liquid in between two very thin membranes. And I'm going to show you just very few examples. I mean, for some of those experiments, let me just comment on that. I mean, there is commercial TM sample holders or even dedicated microscopes available. And I mean, for instance, if you have a dedicated environmental transmission electron microscope, I mean, this would be quite expensive. Even such a TM sample holder already costs like 300,000 or so. But for many of those experiments that I will show you, you can also come up with a prototype. Like if you want to do some in situ mechanical testing, for instance, there are many people who just manufacture, let's say, such testing devices, even for a TM, just by themselves. So because there are no commercial products available, so you can do both. I mean, development of techniques, and development of sample holders, and of such whatever any kind of testing device. If you want to bias, for instance, your material, you want to run the current through while you observe the material. I mean, you just need somehow the equipment, and people do that by themselves, just having like a workshop available. And so, I mean, there are different ways how to conduct in situ experiments. It's just, this is somehow just to advertise, and I know that it might be challenging for you to conduct such experiments simply due to the fact that there might probably not be the equipment available. But I would like to inform you just that this is state of the art. Many people do that all over the world. And I mean, in worst case, you would just need, let's say, a collaboration with another institute or other experts. You just have to get in touch with those. As I showed you, I mean, there's as you know, a very broad range of materials classes people are interested in. There are many questions. These are just a few examples of something about, let's say, mechanical behavior, like optical questions. And this is just very, very selective. What is of interest today is this so-called stimulus. We apply any stimulus to change or to modify a material, which is somehow related, I would say, to the application. I mean, it doesn't make sense to use very small nanoparticles and heat those up to 1,000 degrees, as long as they are not intended to be operated under those conditions, So you have to design your experiment in respect to your material science question that you would like to address. I mean, this is quite clear, I would say. And this is just an overview about what I'm going to present you today. So one part will be about mechanical testing in the scanning and the transmission electron microscope. To conduct such experiments, you can easily understand that in an SEM, you already saw that, you have far more space available, isn't it? Far more space available to design such a testing device, for instance, for mechanical testing, because I mean, it's of this size, probably in a transmission electron microscope, you're highly limited because your full piece gap is so small. I mean, for some of the microscopes we have a Kolb's gap just below 5 millimeters, so 5 mm. Electrical testing, this just means that you conduct like a 2-port or a 4-port measurement that you commonly do on a macroscopic scale. You want to do that on a very localized scale. And I mean, for that, you can either just apply photolithography or electron lithography to generate any kind of structure, electrodes, and you can check those electrodes, or you can make use of those nanomanipulators in a scanning electron microscope, for instance. And here's an example. I will show that later, where we can use a very specialized tool that will bias materials in a transmission electron microscope. This is such a heating stage here, so people heat quite a lot, I would say. This is an example of recrystallization in the microscope, in the scanning electron microscope. And you already saw this example of this plating and the generation of lithium, meaning this is a more operando experiment where we run a battery within the transmission electron microscope to investigate it, to study like the oxidation behavior of pure lithium metal. So this is just an overview. And let me remind you of the fact that whenever you have to think about how to prepare your sample and how to access the sample with your whatever kind of probe or you want to contact that. I would like to remind you that whenever you use FIP preparation for many applications and for many of these in situ studies, you apply FIP milling to generate any kind of structure. From your bulk material, you should be aware of the fact that you change your material, at least the surfaces of your sample, by this ion impact, okay? And you have to keep that in mind that like even metals or ceramics can strongly be modified. And this is just one example how the mechanical behavior of a metal changes by FIP milling. Okay? So these are some pillars, which are, this is one pillar which is generated just by this gallium ion milling. This is already plastically deformed, so there was some stress applied from the top. This is a common pillar test. The glide planes here are an optimized angle of roughly 45 degrees or so. And here you can directly see how the sample behaves. So this is just the stress strain curve of the material. This is somehow, let's say, the bulk or the like undamaged material. And you can see these stresses exceed the observed stresses in this particular, let's say, experiment or in this application here by far. So there is a clear difference just due to the fact that those samples here were prepared using a focused ion. So I mean, you have to be aware of that fact that in this particular case you form this whatever shell layer around that might enhance the strength of the material, that might lead to reduction. On the other hand, if you conduct experiments like in a gas environment, you have to, for instance, you have to be aware of the fact that your electron beam already ionizes your gas or your liquid. So like pH in the liquid might change simply due to your electron beam irradiation. So I mean, you have your electron beam that might change your environment here. You might modify your sample, and so this is what you always have to keep in mind, that for such an in situ experiment, you have to deal with those artifacts. And so you have to overcome those artifacts. This, for instance, is the cross-section of such a metal pillar in the transmission electron microscope, and here you see a very high density of dislocations simply due to the preparation using the ion mill, this ion milling procedure. And after mechanical testing, I mean, this is a very small structure. After mechanical testing, all those dislocations are gone because you have a huge surface area available, and they just moved out to the outer surfaces and just disappeared. So this is somehow, this is probably the material how it would have been. This is just some artifacts generated by the focused ion beam. In principle, you don't want to have that, so this is what I mentioned. You somehow have to consider all those effects. But nonetheless, people conduct in situ experiments. There are many publications, and it's a very hot topic because people want to correlate, like let's say, the structure, the chemistry of a material on the one hand side, and like the functionality or some degradation of the material on the other. And you might do that ex situ, just to like anneal samples in the furnace and just test in the electron microscope over certain periods of time, or you can do that like during heating experiment within the microscope. This is some, for instance, some mechanical testing device. In this particular case, this is just one of these nanomanipulators, like one of these miniaturized robot arms. And in this particular case, here is like a diamond indenter mounted to that. The sample, it faces this indenter here. And what they make use of, this is just a spring table. These are spring tables, so you mount your sample on one side of this spring here. You know the spring constant, and just by measuring, let's say, this the relative shift value, and then you can directly correlate it to a force. You don't necessarily need a force measurement device here to come up with a nanomechanical or like such a testing experiment. Because I mean, to realize a force measurement here that might be quite demanding, to make use of such, let's call it a simple spring table where you know the spring constant, this is much easier. But if you want to go down in scale, people use MEMS devices. I mean, there's a vast variety of MEMS devices available for mechanical testing, for electrical testing, for heating. Because I mean, those are small, those can be easily put into a TM sample holder, in a dedicated TM sample holder, to conduct any kind of like measurement. And here, for instance, you measure, let's say, the strain or the shift, for instance, by a capacitance as you apply a certain load. And so there are many examples and devices. So let me just show you one example why this might be of interest. So this is a transition, a phase transition in just silicon. This is just silicon pillars that are prepared. On the left-hand side, this is at room temperature, and all of you know that the silicon wafer behaves like it's brittle. This is what happens here. On the left-hand side, you just apply stress. It's elastically deforming at some point because you have some shear stress. It just chips off. Here on the right-hand side, you see plastic deformation of the silicon wafer. There's some slip occurring here. It's hardly visible. And so, I mean, this is a totally different behavior, isn't it? At room temperature, at high temperature, because of some phase, like some transition within the material, or this plasticity and this ductile behavior. And I mean, this is what people are interested in. For metals, for instance, people are, if you do a stretch test, because you want to drill holes, you want to see, you directly want to observe the behavior, how the material, like let's say, flakes off, how it comes off, and how these tiny pieces are formed if you want to have like a machinable material. This is a test, just a scratch test in the scanning electron microscope. And I mean, you can do all those tests on various scales. Like this is on the micrometer, far micrometer scale, and you can go down to the like 10, 20, 50 nanometer scale. This is another example of mechanical testing in a scanning electron microscope, because people are also interested in mechanical behavior of nanoparticles, for instance. So you want to do like some indentation on individual nanoparticles. This is a testing device where you have an indenter. This is a piezo-driven indenter here. The device was developed at Erlangen University. There's a huge group working on nanoparticulate materials, and they wanted to come up with such a testing device to conduct like indentation and like mechanical testing of nanoparticles. They also make use of a spring table here, but they have a load cell installed to that. You mount your sample here with, let's say, your nanoparticles just dispersed, and you apply just a certain load to those nanoparticles in that part. And this was self-made by the group. Let me just show you. So the whole system was developed. This is a video which you don't have in your printout. So this is like an advertisement what they prepared this video. And this is our substrate here. This is our diamond indenter. You can see these are all the nanoparticles. This particular project is about the plasticity of glass particles. So this is silica. This is your indenter. The size of these particles is of the order of a few hundred nanometers already. You see this slightly, let's say, brittle behavior, and depending on the density of these particular particles, they are synthesized by a wet chemical route, and they exhibit a certain porosity. So this is quite brittle. The other one was a different particle. And I mean, this is, you can just test not only single particle, by this you can do statistics. You can indent, let's say, 10,000 particles. That just takes you one day. And you can come up even with the load displacement curve by that, because you know the load, you know the displacement, and then you can really come up with some quantitative data on the plasticity, for instance, of such particles. And the reason why they did it on these particles, I mean, this group is also in a collaborative project interested in the plasticity or the behavior of glass in general, and because I mean there are many applications for glasses, and so just depending on the thermal treatment, I mean there are strong differences. This is another example of the mechanical testing in a focused ion beam, and some of you might already have seen. Yeah. Oh. Might have already seen such images or such videos. I mean, most of these videos are online on, like, let's say, YouTube or other channels. You can easily just search for such in situ experiments, and you'll find many examples. This is just a testing of such bending, like a bar. So the bar was generated using the focused ion beam. People might be interested in this area, like, because there is an interface, or you might want to test the bulk properties of the material. This is your indenter here. You can easily measure the force here. In this particular case, you know the geometry because it's well defined. And you might be able to come up with some quantitative data on bulk properties, or on a very localized scale. Because I mean, if you have certain homogeneities, like an interface in your material, you might want to test that. So to understand probably like flaking of a coating, if you're interested in that, I mean, you would like to know where this flaking occurs. It could be in the substrate, directly at the interface, it could be in your coating. So this is what people are interested in. This is how this 3D bar, or the 3D like the bar looks like after the flip preparation. And I mean, as I mentioned, you always have this surface layer, this damaged surface layer, and you have to somehow get some idea how this affects your experiment. Let me just show you, let's say, one example. So people, based on this geometry, people measure the displacement here. So the video is running, it takes a while. Now there is some, let's say, elastic deformation, and at the final state, a crack will occur or will develop here, and it will just fail. Okay? From this displacement and the load that you measure, you directly, you might be able to derive a stress strain curve, and this is what like people working on metals are interested in. So this was SEM. Let me show you one example in the transmission electron microscope. Before I'm going to start this video here, I would just briefly explain how this TM sample holder looks like. So this is the frontmost tip of the sample holder, and you span just a TM sample right in between. In this particular case, there is a movable part in this TM sample holder coming from like the far back of the sample holder, the far end, and by applying like some stress in this direction, you convert that in some tensile stress in the perpendicular direction. I mean, there are different realizations how you might come up with a nanomechanical testing device. This is only one way. And here on the left-hand side, there's a video where people demonstrated the movement of dislocations. I mean, dislocation movement in principle is pretty fast. So it's of the order of the speed of sound in matter, which would hardly be observable. This is a special material, so that was irradiated. This is a stainless steel irradiated, and that caused some hardening. So the movement of dislocations is strongly limited. And this is how you see that in bright field TM imaging, where you can see all these individual dislocations moving through the material. And I mean, this is just the movement in one direction. If you're interested in like the interaction of dislocations, and you are interested in hardening within the material due to like nucleation and multiplication of dislocations, you can observe and you can watch that in situ. You know, so you can learn a lot about your material while you operate it, or while you, like, let's say, stress it. Okay, and I mean, this was just a very few examples of mechanical testing in the scanning and transmission electron microscope. But I would say everything that comes to your mind might be applicable, and you just have to think about how to realize that. This is a heating stage for the scanning electron microscope. This is a commercial one. from probably from Papa and Weiss, it's a German manufacturer, and you might be interested to use such a device, or you might either have a ceramic heater in this particular case because you want to go up to very high temperatures. And you have a shielding plate here that you can close, even close. I mean, you always have to keep in mind that we are very close to our pole piece, isn't it? Our objective lens in the scanning electron microscope. You somehow have to keep in mind that if you heat up to like 1000 degrees C, even your secondary electron yield might be totally different. So you have always to think about which signals to utilize for your in situ experiment. So this is how this heater looks like at pretty high temperature. I mean, we are for many applications in high vacuum to conduct those experiments. If you, let's say, if you work under a certain environment, under a certain gas environment, you always have to keep in mind that your sample temperature, for instance, might differ from your preset sample, from your preset heater temperature, because you only measure the temperature in there, and you have a certain surface, and you just watch the surface. But if you have a gas environment, in very high temperatures, there might be thermal losses. Isn't it at very high temperatures we have radiational losses, so the sample surface might be colder. And on the other hand, in environment you have convection and the transfer to the gas environment. And it turned out, so there were just some very few recent publications in the field that environmental TM, for instance, if you have a very small sample, very thin TM sample, you can easily imagine if you heat from the outside, the heat has to be transported to your innermost region. But in the innermost region, you have a huge surface available to boost energy, and you have a very limited cross-sectional area available to transport and to add energy. Okay, so and during environmental TM measurements, the temperature of your original or of your region of interest might be off by a few hundred Kelvin from your preset temperature of your heater. So in principle, for such experiments, you would need, but this is very challenging, you would need certain ways how to measure the temperature on a very localized scale, either by, let's say, electron diffraction, because I mean thermal expansion, or heat causes thermal expansion that causes a shift of your lattice planes or change of your lattice parameter, and by that you are able to observe changes of your diffraction pattern and your spacings in your diffraction. But you have to be very accurate to achieve that. You have to, like, the thermal expansion coefficients of common crystalline materials of the order of 10 to the minus 6 to 10 to the minus 5 or so, and to observe any temperature change of a few Kelvin necessitates such an accuracy in electron diffraction. And we just published on that 1 year ago. So one of our students spent a lot of effort to achieve that accuracy, let's say, in Debye diffraction. So just by this ring pattern acquisition of nanoparticulate materials, we were able to measure the temperature with an accuracy of 3 to 4 Kelvin. And I mean, you need ways to measure the temperature on a local scale. You should never rely just on this preset value or on the measurement of your heating device. So let's say people use it quite a lot to conduct, let's say, electron backscatter diffraction, for instance, because many people working on metals are interested in things like recrystallization. For instance, this is a recrystallization experiment here. This is the EBSE map that evolves over time. Here in the phase transformation, so this what shows up here is an FCC phase in this particular material, just upon heating. The temperature is here quite pretty high, it's already 900 degrees Celsius. You hardly see it, sorry for that. But in principle, this is what people do. We already saw this slide here. This is the same holds for a transmission electron microscope. And there are many, let's say, examples why people heat materials. And I just want to show you 2 opportunities how to heat samples in a transmission microscope. Because in an SEM it's quite simple, you just use a ceramic heater, you put your sample on top. For TM there are 2 ways. One are so-called furnace heater. So this is where you heat this whole part where you mount your TM sample. So you heat your sample from the outside. Okay? There's one big disadvantage here is this evolving heat loss at higher temperatures. And if you want to conduct, for instance, any chemical analysis, you use your EBS detector. you will run into trouble with infrared light on your EDS detector. So this is a big disadvantage. You cannot do chemical analysis at high temperatures. Another disadvantage is that you might end up with a strong drift of your sample, because whenever you heat, I mean, you introduce stresses, and by that, I mean, drift might occur. People are interested in atomic resolution imaging, so with this, you can hardly realize atomic resolution imaging. But nonetheless, this is, on the left-hand side, another video of the crystallization of silicon. This is a video that Balaji recorded quite some years ago of this Lyle sample. So in this particular case, this is the crystalline silicon that appears. On top, there is this second layer, so we penetrate with our electron through the sample. And this was just to see some slight movement. In principle, if you want to publish such data, you would always correct for such drift or such movement to come up with a steady video. Okay? The temperature that you can achieve with such holders goes up, let's say, to above 1000 degrees Celsius. And I mean, there's another way how to heat in a transmission electron microscope, and this is to utilize such MEMS-based heater chips. In this particular case, this is the solution heater chip. So you just introduce this heater chip, you contact it, and you just simply run a current through such a metallic nanostructure. And due to the resistivity of the nanostructure, heat evolves. And I mean, they apply a current to introduce the heat, and they measure with another 2 ports, they measure the resistivity of the structure, and the resistivity depends on the temperature, and so they are able to calibrate this temperature. And for high vacuum experiments, indeed this preset temperature corresponds very well to the measured temperature which we got from our diffraction experiments. So this is quite good. There's another example on the left-hand side, but this means that while you can reuse the sample holder, this furnace holder, for any further material, whenever you conduct an experiment and you disperse nanoparticles or you apply a fit lameller onto this heater chip, you would need to use another heater chip for your next experiment. And then those heater chips might even be damaged at the very high temperatures. So this is like a spare part of these heater chips. On the left-hand side, there is another example of the recrystallization of a nanostructure here on the atomic scale, and you see that there is hardly any drift. So this is atomic resolution imaging. You get a static image. You don't have any drift of those samples. So this is the big advantage of using such MEMS-based heater chips, because you just heat on a very localized scale. The evolving heat and the evolving radiation at high temperatures is strongly reduced, so you can do EDS at temperatures far above 800 degrees Celsius. And I mean, if you're interested in any kind of metallic or whatever kind of structure, you can do a lot simply by heating. And there are quite a few examples. This is, let's say, a compilation of what people do by heating in a transmission electron microscope. You will see many examples. This is the debetting of a metal film. So there's gold. You hardly barely see it here because it's a pretty thin gold film. This is a scanning TM image. And people are interested in, for instance, the debetting behavior of metal films on surfaces. Because if you simply think, for instance, a hard drive, which is metal coated, the older ones, and you end up with a change of the metal distribution of your structure, just upon heating, your device might fail. So there are many applications where people are interested in the debetting. If you generate, like, let's say, materials for catalysis, people are interested in, like, the behavior of the distribution of the, for instance, of the catalytic particles on the ceramic support, like porcelain, phosphide-ribene, things like that. So people want to understand why materials fail, for instance, and so this is why they conduct heating. How structures form. This is another application. How structures form upon heating. This is the recrystallization here of germanium. This is the growth of nanotubes in an environmental TM. So there is even some reaction gas introduced to facilitate the growth of nanoparticles. This is this crystallization of silicon that I already showed. This is the reduction and the structure formation of a fuel cell anode. And here on the right-hand side, you will see one example of the growth of graphene on the surface. Let me just start those videos. So this is the debetting at high temperature, so in high vacuum, 350 degrees C. And in this particular case, one of our PhD students was interested in, like, let's say, the formation of those structures and the retraction of all those struts in between. So, because commonly, if you conduct such an experiment ex situ, you would just investigate your starting or your original state, and after a certain period of time, you would look at the sample again, isn't it? And you would end up just probably with a model. And here, I mean, the question was about whether the material, the gold, is transported via surface diffusion, via interface diffusion, or I mean, there are many ways how to redistribute the metal, and this all depends, I mean, on what's going on during this relative process, isn't it? This is just the recrystallization here in high vacuum at different temperatures of this uppermost tip. So this is liquid here, now it crystallizes. And in principle, that occurs atomic layer by atomic layer if you look carefully. So I mean, structure formation, it's not that there's just something going on the bulk and it recrystallizes, but coming it nucleates at some point, and then atomic layer by atomic layer, the material crystallizes. So this is, for instance, a transformation of an amorphous phase to crystalline phase. At the right-hand side, this is, as I mentioned, the growth of carbon nanotubes. There are catalytically active particles. We introduce the gas, reaction gas, to observe that. This is another experiment in high vacuum here. This is this recrystallization of silicon. You see this bent contours and some diffraction contrast. So this is the aluminum film that Balaji may utilize for this Allyl process. And this is already this crystallized silicon layer. In this particular case, the question came up how the aluminum from this lower layer is transported into the upper layer. Just, let's say, through this diffusion barrier that was deposited as well. And it turned out that in some areas, which you hardly see here, that this diffusion barrier layer just breaks, and you have such a very rapid push-up of the silicon because there is some stress involved. Stress occurs, and that just causes the failure of this interlayer. This is the reduction of a nickel zirconium oxide anode of a fuel cell, where you see that the nickel, these are some nickel grains, in between there's some zirconium oxide grains. The nickel gets reduced here. This is done in hydrogen environment in a microscope at 240 degrees, and I mean, by that, people are able to follow the reduction. And if you cycle and if you operate a fuel cell, the question is always, whether those materials fail or not. Because if you, let's say, reduce in the first step and then you quench or you change the temperature of your fuel cell, you might even end up with a local oxidation and some redox cycling of your catalytically active material. And if that does not densify anymore and you have a composite material, inherent stresses might occur, and that might cause just cause the flaking or the degradation of such a fuel cell anode.
So we can see the structural phase transition.
Pardon?
We can see the structural phase transition.
Yeah, in many effects, this is like the bright field here image. You see, this is the nickel. If you reduce nickel oxide to nickel, you gain volume because you lose all your oxygen, so the volume is smaller. This is why pores form in this reduced nickel oxide. But you have to think about what happens if you re-oxidize that.
Yes.
If you oxidize that in another step, for instance, it doesn't necessarily mean that all the pores, vanish. So just by this oxidation of your nickel, so meaning that some of these pores might even remain in the material. If pores remain, the volume of one grain is larger than before, and that might cause stresses, for instance. Like people are highly interested in failure of batteries or fuel cells, so you want to do such, let's say, cycling within the microscope. On the right-hand side, there's this growth of graphene. As you can see, there is layer by layer. You see some new layer of graphene forms on the surface. This is already multiple layers of carbon. This is a metal substrate here. This is done also by providing a certain reaction gas that provides carbon. The carbon dissolves in this metal here, and it just causes, upon supersaturation, it just causes the formation of a new layer of graphene on the surface. So this is what let's say, what people want to do and what people still do. And I mean, this is another example on the atomic scale, just to show you, this is just some repetition about what people nowadays do and what they are able to do. I mean, this is just the observation of any kind of change of the material down on the atomic scale, isn't it? And I mean, there are, I would say, two advantages to do that with a parallel beam, you know, with a parallel beam illumination in HRTM mode or in conventional TM mode, because it's quite fast. You just record one image after the other, isn't it? In STEM mode, you always have to deal with slight drift, and you have to deal with like prolonged exposure times. This is like most of these examples which I show, and just, you know, the data is just recorded in conventional TM mode, right, in dark field mode, or HRTM mode. But there are also examples like people, let's say, do STEM activities. This is another field. It's about environmental microscopy. Environmental means that we want to apply almost any kind of environment. That doesn't necessarily mean to apply like air or humid environment. In this former slide, you already saw that people, you know, introduce reaction gases here for the growth of graphene. You introduce hydrogen to reduce materials. And as long as, I would say, your vacuum system or your environmental microscope withstands your gas that you want to introduce or your liquid, you might be able to do that. And environment doesn't also necessarily mean to introduce a gas environment, because you could think about to work in a liquid or, you know, in like liquid environment. And how people realize that is, I mean, you have to separate, in the scanning electron microscope, for instance, you have to separate your chamber with at like increased like partial pressure of your gas from your electron column. Because I mean, we have our electron source. The electron source, like a field emission electron source, has to be operated under ultra high vacuum conditions. And I mean, you cannot let any gas diffuse up to your electron source, isn't it? You want to keep your electron column free of that gas because of inelastic scattering, and elastical scattering in this gas environment is just a question about how you conduct those experiments. But nonetheless, 30 kilo electron-volt electrons are able to penetrate through, let's say, already a pretty thick layer of gas without any, like I would say, negligible or very low, you know, loss of resolution on your sample. So I mean, any inelastic and elastic scattering would cause a broadening of your beam in a scanning electron microscope, but up to a certain pressures, I would say. I mean, this is, you can see, in this particular case, it goes up to 3000 Pascal. This is 30 millibar. I mean, 30 millibar, this is not a really high pressure compared to 1 bar atmosphere, isn't it? To 1 atmosphere. So, but people, they introduce like humidity, water vapor, they introduce just gases like hydrogen, oxygen, nitrogen. It depends on what you're interested in. What we have here in between is we have a so-called differential pumping apertures. So you have very small limiting apertures so that the gas from here to there or the diffusion of gas is just strongly limited by apertures. And you add additional pumping equipment, you add several of those apertures, and you add additional pumps to introduce a very steep drop of your pressure, okay, towards your electron current. So you need somehow many more pumps, meaning that in this particular case, you just flood the whole chamber. You might also introduce, let's say in a scanning electron microscope, you might also think about to introduce your gas on a very localized scale by using one of the gas injection systems, for instance. Meaning you have this, like in Focus-Einbeam, you might have such gas injection systems right available, and then you can introduce humidity on a very localized scale by just introducing this needle, this injection needle, and to apply this gas environment just on your sample surface. So you can use some of these robot arms to equip those just with a fine tube to introduce gases on that scale. Unfortunately, doing it this way, you currently don't know the local pressure of the gas because they just, you know, it just gets dissolved. And so this is like why there are dedicated microscopes available. And even the EVO microscope that you saw in the live demonstration, the scanning electron microscope that was on the left-hand side, which we used for the live demos, this is not necessarily a high vacuum tool. This is already a so-called variable pressure microscope. And with this microscope, you can introduce gases up to this pressure of 30 millibar. So that microscope already has this differential pumping aperture. For instance, if you're interested like in biological specimens, you would like to introduce certain humidity to the surface, then you can do it with this specific tool. So this is already a specialized microscope. So this is not just a high vacuum tool. Let me just show you very few examples of what people do in gas environment. I mean, this is a very simple one. This is heterogeneous nucleation of ice. This is ice due to water vapor at the microscope on a cold surface. And this is just how ice crystals form or ice layer forms on the surface. Okay? So pretty simple experiment. I must say I don't know exactly why they did it, but there are many other examples. This is the melting of salt at high temperature in the scanning electron microscope. Just another example. So this is a liquid phase here. This is crystalline, and just the liquid phase just covers now this liquid phase. This is upon cooling, recrystallization of the material just upon cooling. You see that the structure looks quite different.
So how it is possible cooling leads to this crystallization?
I mean, if you have
heat or any lower sample for crystallization?
no, I mean, yeah, but no, what you have here, if you have a purely liquid phase, and this is what like working on metals, what they know, if you have a phase diagram, and if you have a liquid phase field, and you cool down, then nucleation will happen. So nucleation will happen, and crystals will form if your crystalline phases stay at lower temperatures. Meaning that first you raise the temperature to melt the material. If you lower the temperature, you just follow like phase diagram, and then how many nucleation occurs. And the crystallization happens. So this is quite common. There are two more, like I would say, examples which are more relevant, like in applications. This is a copper surface, and it's a very nice and clean sample. And I just got these from a colleague from Berlin, Mark Willinger. These are not published, but nonetheless, I would like to share those here. So this is just a copper surface. In oxygen environment at slightly higher temperature. And so this is about the oxidation of a metal. And you will see that this is also does not happen all over the surface. So this is the copper oxide that forms on the surfaces. This is secondary electron imaging mode. And you see this nice growth, like let's say, of all those copper oxide crystallized. In this particular case, up to that state, it's not the whole surface is oxidized, isn't it? And the same material under, let's say, reaction conditions in a redox reaction. So in this particular case, hydrogen and oxygen are introduced. In the former case, it was only oxygen at these temperatures. And this is now like a, let's say, a chemical reaction because copper is it's catalytically active. And this is how such a catalytically active surface might behave. So this is, it's not that you have like certain like oxidation and reduction on the atomic scale. This is a pretty severe change of the morphology of a whole surface just during such a reaction. You see some areas which get oxidized, some areas which get reduced, and this is such an interplay between local oxidation and reaction and reduction of such a catalytically active surface on a larger scale. But how can we realize environmental TF? I mean, we have limited capability, so there's less space available. They do it in a pretty similar way. There might be either dedicated microscopes available, where you just introduce the gas environment on a very local scale, just right at your sample. So we insert our sample holder, we have our objective lens here, 2 pieces, and we have these differential pumping apertures all over the, just distributed in our electron column. We have additional pumps attached and by that we are able to achieve certain pressures up to, let's say, 50 millibar. I mean, 50 millibar for catalytic reactions, 50 millibar is quite low. Catalytic reactions, they occur or they happen at pressures of 2 bar or so, or 3 bar. And there's quite a difference in your material. If you watch the material at 50 millibar or at 3 bar, there are a few examples already published. But nonetheless, if you want to observe, let's say, this growth of your nanotubes or so, this is what the people use for at Stanford to conduct such experiments. So this is a very, very specialized microscope. And you have two operation modes. You can either operate it in this environmental mode, or you can just pump it down to high vacuum conditions. So meaning that all of these environmental instruments you can also use under high vacuum. The other way, if you want to achieve far higher pressures, you might want to use such a MEMS-based chip. The advantage is of such a MEMS-based chip, so you introduce the gas just using you have very, very fine, very narrow tubes available, and you combine two chips, two membranes, very thin membranes, silicon nitride membranes, and you confine your gas environment in between these two chips. So you have a sealing O-ring, you introduce your gas from the side, so just through your whole sample holder, and you just mount that together. The big advantage of such a dedicated microscope, although it just allows for very relatively low pressures, is that you can combine it with almost any other in situ holder. So you can easily do a straining experiment in hydrogen environment, for instance, or you can do a heating experiment with any type of heating holder, or you can bias your sample just by using a biasing holder. Here, you are always limited by the functionality of the chips. This is already a combination of such an environmental holder with a heater chip. So many people are interested to conduct experiments at high temperatures in a certain gas environment. So you have to think about how to realize that. This specific net solution holder allows for both, and the pressures that are, you have to remember, or you have to imagine that those membranes are very small. So meaning even at 2 bar pressure, this is like a common range that you might achieve, even at 2 bar pressure, the force to these very thin membranes is so small, so low, that those wouldn't fail, So this is the reason why you can go to far higher pressures. And the distance, or the thickness of your gas, layer is commonly of the order of a few micrometers. So you have to penetrate with your electron beam through your confining membranes, through the gas environment, and that's finally through your sample. But nonetheless, at 200 or 300 kilo electron volts, you get quite decent atomic resolution data of that. This is one example that you already saw. This is the study on this, the lithium and the corrosion of the lithium, and I will not explain that in very much detail. I would just like to share just a second time this corrosion of lithium in wet environment. This is our metallic lithium here, and this is just this corrosion layer, which is highly open porous. And by such studies, we were able to understand somehow this reaction, or these reactions going on and causing this drastic degradation, like let's say of batteries. This is just one example, one holder for liquid environment. So you have a very specialized tip of the sample holder. This is in a scanning electron microscope. You have like an inlet and outlet for your gas, for your liquid environment. And in this particular case, you also confine your liquid environment using 2 membranes, and you work in transmission mode here, even in a scanning electron microscope. The same holder or similar tip you may use in a transmission electron microscope. You have a dedicated holder for GL microscope in this particular case, and you just drive your solvent or your liquid, like water or so, just through this area where you just have these 2 membranes, and by that you're able to observe or to watch any kind of structure formation, the growth of nanoparticles, or any kind of changes within this liquid environment. And as I mentioned already, you have to think about how the electron beam affects this liquid phase, for instance, because you might can easily imagine that you ionize all those species because you have the interaction not only with your sample that you're interested in, but as well with your liquid environment, and by that you might change, for instance, the pH of water. Because you introduce ions, the ion concentration is higher, by that the pH is different. Meaning if the pH is different, if you want to observe any growth or of particles, that might already cause some trouble. This is the growth of gold structures, like from a solution and some reaction products, and you can see that there is somehow different growth modes of these dendritic structures in this particular case, and of this continuous growth, let's say, of more homogeneous nanoparticles. And I mean, if you just see the final state deposited from a solution just onto your, let's say, TM grid, you might not understand what's going on and why those different structures form, for instance. I must say that such measurements in the liquid environment are even more challenging than measurements in gas environment, because this interaction, I would say there are very few publications about this interaction with this liquid environment. This is quite challenging. This is a very specialized sample holder, let's say, to conduct electrical measurements in a transmission electron microscope. I mean, you can easily imagine that in a scanning electron microscope, it might be quite easy. You might even be able just to contact your structure using wires, wire bonding, using electron or any kind of lithography. And if you're interested in the electrical behavior of nanostructures, you might just disperse them onto the electrodes, and just due to statistics, there might just be some of the nanostructures lying in between your electrodes. In this particular case, this is a very specialized sample holder to conduct electrical measurements, two-pot measurements on a very localized scale in a transmission electron microscope. So in this particular case, the TM sample is mounted on the left-hand side, and on the right-hand side you just have a metal tip installed, and you can manipulate your sample and move your sample and contact very, very locally. This is one example where we measured just the switching of TC and Q nanowires, so this is more an organic molecule, and by introducing currents up to a certain field strength, you will see that the resistivity changes. The question was, people want to make use of those switching materials to realize circuits on a localized scale, and so we approached with this metal tip here on the right hand side, or the other way we approached this metal tip with our sample by just moving our sample, and just by contacting individual nanowires, we were able to demonstrate this hysteresis, so this switching behavior depending on the applied current. So you can do that on the localized scale. You can directly contact individual nanostructures. This is what you can do in a scanning electron microscope as well, just by using such nanomanipulators, for instance. And I mean, this is only one example why people want to contact materials. I mean, if you have a nano device that you want to test, or a fuel cell or whatever, any kind of battery, people are interested in the electrical behavior. So there are many questions why people do that. There's a very nice example. I couldn't find it. I couldn't find the movie yesterday. There's a very nice example. People might be interested in electromigration. So whenever you run a current through a device, metal species might migrate, and this causes the failure of devices or metal contacts after a certain period of time. And there are people who even just prepare TM samples where, let's say, your metal channel or your metal contact is confined, and they run a current and they watch this electromigration in real time to see where the failure occurs. And I mean, this is quite demanding, because I mean, you want to keep all the material intact, just to have your metal channel or your metal contacts embedded in your material while you are penetrating with the electron beam through the structure. I mean, this is where you use the focused ion beam point. I mean, we already saw that for many of these in situ studies, you make use of a focused ion beam to generate the samples. And it always depends on the material that you work on in the study that you want to conduct. In principle, there are many ways. And I would like just to encourage you to think about, so if you have any idea, and let's say, any question to that, I mean, we are open for discussion, but biology knows people in that field, we know people in that field, and I mean, it's just up to you, I would say, to initiate those studies. And with that, I would like to finish for today, so we are right in time for our coffee break today. And yeah, with that, this was the last slide, I would say, of our course. With that, I would like to thank you for your attention during the last 2 weeks. Load, the displacement, and then you can really come up with some quantitative data on the plasticity, for instance, of such particles. And the reason why they did it on these particles, I mean, this group is also in a collaborative project interested in the plasticity or the behavior of glass in general, and because I mean there are many applications for glasses, and so just depending on the thermal treatment, I mean there are strong differences. This is another example of the mechanical testing in the focused ion beam, and some of you might already have seen. Yeah. Oh, might have already seen such images or such videos. I mean, most of these videos are online on, let's say, YouTube or other channels. You can easily just search for such in situ experiments. You will find many examples. This is just a testing of such bending, like a bar. So the bar was generated using the focused ion beam. People might be interested in this area, because there is an interface, or you might want to test the bulk properties of the material. This is your indenter here. You can easily measure the force here. In this particular case, you know the geometry because it's well defined. And you might be able to come up with some quantitative data on bulk properties, or on a very localized scale. Because I mean, if you have certain homogeneities, like an interface in your material, you might want to test that. So to understand probably flaking of a coating, if you're interested in that, I mean, you would like to know where this flaking occurs. It could be in the substrate, directly at the interface, it could be in your coating. So this is what people are interested in. This is how this 3D bar, or the 3D, the bar looks like after the flip preparation. And I mean, as I mentioned, you always have this surface layer, this damaged surface layer, and you have to somehow get some idea how this affects your experiment. Let me just show you, let's say, one example. So people, based on this geometry, people measure the displacement here. So the video is running, it takes a while. Now there is some, let's say, elastic deformation, and at the final state, a crack will occur or will develop here, and it will just fail. Okay? From this displacement and the load that you measure, you might be able to derive a stress strain curve, and this is what people working on metals are interested in. So this was SEM. Let me show you one example in the transmission electron microscope. Before I'm going to start this video here, I would just briefly explain how this TM sample holder looks like. So this is the frontmost tip of the sample holder, and you span just a TM sample right in between. In this particular case, there is a movable part in this TM sample holder coming from the far back of the sample holder, the far end, and by applying some stress in this direction, you convert that in some tensile stress in the perpendicular direction. I mean, there are different realizations how you might come up with a nanomechanical testing device. This is only one way. And here on the left-hand side, there's a video where people demonstrated the movement of dislocations. I mean, dislocation movement, in principle, is pretty fast. So it's of the order of the speed of sound in matter, which would hardly be observable. This is a special material, so that was irradiated. This is a stainless steel irradiated, and that caused some hardening. So the movement of dislocations is strongly limited. And this is how you see that in bright field TM imaging, where you can see all these individual dislocations moving through the material. And I mean, this is just the movement in one direction. If you're interested in the interaction of dislocations, and you are interested in hardening within the material due to nucleation and multiplication of dislocations, you can observe and you can watch that in situ. You know, so you can learn a lot about the material while you operate it or while you, like, let's say, stress it. Okay, and I mean, this was just a very few examples of mechanical testing in the scanning and transmission electron microscope. But I would say everything that comes to your mind might be applicable, and you just have to think about how to realize that. This is the heating state for the scanning electron microscope. This is a commercial one from probably from Kaplan and Weiss, it's a German manufacturer, and you might be interested to use such a device, or you might either have a ceramic heater in this particular case because you want to go up to very high temperatures. And you have a shielding plate here that you can close, even close. I mean, you always have to keep in mind that we are very close to our pole piece, isn't it, of our objective lens in the scanning electron microscope. You somehow have to keep in mind that if you heat up to like 1000 degrees C, even your secondary electron yield might be totally different. So you have always to think about which signals to utilize for your in situ experiment. So this is how this heater looks like at pretty high temperature. I mean, we are for many applications in high vacuum to conduct those experiments. If you let's say if you work under a certain environment, under a certain gas environment, you always have to keep in mind that your sample temperature, for instance, might differ from your preset sample, from your preset heater temperature, because you only measure the temperature in there, and you have a certain surface, and you just watch the surface. But if you have a gas environment, at very high temperatures, there might be thermal losses. Isn't it at very high temperatures we have radiational losses, so the sample surface might be colder. And on the other hand, in environment you have convection and the transfer to the gas environment. And it turned out, so there were just some very few recent publications in the field that environmental TM, for instance, if you have a very small sample, very thin TM sample, you can easily imagine if you heat from the outside, the heat has to be transported to your innermost region. But in the innermost region, you have a huge surface available to lose energy, and you have a very limited cross-sectional area available to transport and to add energy. Okay, so and during environmental TM measurements, the temperature of your original or of your region of interest might be off by a few hundred Kelvin from your preset temperature of your heater. So in principle, for such experiments, you would need, but this is very challenging, you would need certain ways how to measure the temperature on a very localized scale, either by, let's say, electron diffraction, because I mean thermal expansion, or heat causes thermal expansion that causes a shift of your lattice planes or change of your lattice parameter, and by that you are able to observe changes of your diffraction pattern and your spacings in your diffraction pattern. But you have to be very accurate to achieve that. And you have to, like, the thermal expansion coefficients of common crystalline materials of the order of 10 to the minus 6 to 10 to the minus 5 or so, and to observe any temperature change of a few Kelvin necessitate such an accuracy in electron diffraction. And we just published on that 1 year ago. So one of our students spent a lot of effort to achieve that accuracy, let's say, in Debye diffraction. So just by this ring pattern acquisition of nanoparticulate materials, we were able to measure the temperature with an accuracy of 3 to 4 Kelvin. And I mean, you need ways to measure the temperature on a local scale. You should never rely just on this preset value or on the measurement of your heating device. So let's say people use it quite a lot to conduct, let's say, electron backscatter diffraction, for instance, because many people working on metals are interested in things like recrystallization. For instance, this is a recrystallization experiment here. This is the EBSD map that evolves over time. Here in the phase transformation, so this what shows up here is an FCC phase in this particular material, just upon heating. The temperature is here quite pretty high, it's already 900 degrees Celsius. You hardly see it, sorry for that. But in principle, this is what people do. We already saw this slide here. This is the same holds for the transmission electron microscope. And there are many, let's say, examples why people heat materials. And I just want to show you two opportunities how to heat samples in a transmission microscope. Because in an SEM it's quite simple, you just use a ceramic heater, you put your sample on top. For TM there are two ways. One are so-called furnace heater. So this is where you heat this whole part where you mount your TM sample. So you heat your sample from the outside. Okay? There's one big disadvantage here is this evolving heat loss at higher temperatures. And if you want to conduct, for instance, any chemical analysis, you use your EDS detector, you will run into trouble with infrared light on your EDS detector. So this is a big disadvantage. You cannot do chemical analysis at high temperatures. Another disadvantage is that you might end up with a strong drift of your sample, because whenever you heat, I mean, you introduce stresses, and by that, I mean, drift might occur. People are interested in atomic resolution imaging, so with this, you can hardly realize atomic resolution imaging. But nonetheless, this is, on the left-hand side, another video of the crystallization of silicon. This is a video that Balaji recorded quite some years ago of this Lyle sample. So in this particular case, this is the crystalline silicon that appears. On top, there is this second layer, so we penetrate with our electron through the sample. And this was just to see some slight movement. In principle, if you want to publish such data, you would always correct for such drift or such movement to come up with a steady video. Okay? The temperature that you can achieve with such holders goes up, let's say, to above 1000 degrees Celsius. And I mean, there's another way how to heat in a transmission electron microscope, and this is to utilize such MEMS-based heater chips. In this particular case, this is the solution heater chip. So you just introduce this heater chip, you contact it, and you just simply run a current through such a metallic nanostructure. And due to the resistivity of the nanostructure, heat evolves. And I mean, they apply a current to introduce the heat, and they measure with another two ports, they measure the resistivity of the structure, and the resistivity depends on the temperature, and so they are able to calibrate this temperature. And for high vacuum experiments, indeed this preset temperature corresponds very well to the measured temperature which we got from our diffraction experiments. So this is quite good. There's another example on the left-hand side, but this means that while you can reuse the sample holder, this furnace holder, for any further material, whenever you conduct an experiment and you disperse nanoparticles or you apply a fit lameller onto this heater chip, you would need to use another heater chip for your next experiment. And then those heater chips might even be damaged at the very high temperatures. So this is like a spare part of these heater chips. On the left-hand side, there is another example of the recrystallization of a nanostructure here on the atomic scale. And you see that there is hardly any drift. So this is atomic resolution imaging. You get a static image. You don't have any drift of the sample. So this is the big advantage of using such MEMS-based heater chips, because you just heat on a very localized scale. The evolving heat and the evolving radiation at high temperatures is strongly reduced, so you can do EDS at temperatures far above 800 degrees Celsius. And I mean, if you're interested in any kind of metallic or whatever kind of structure, you can do a lot simply by heating. And there are quite a few examples. This is, let's say, a compilation of what people do by heating in a transmission electron microscope. You will see many examples. This is the debetting of a metal film. So there's gold. You hardly barely see it here because it's a pretty thin gold film. This is a scanning TM image. And people are interested in, for instance, the debetting behavior of metal films on surfaces. Because if you simply think, for instance, a hard drive, which is metal coated, the older ones, and you end up with a change of the metal distribution of your structure, just upon heating, your device might fail. So there are many applications where people are interested in the debetting. If you generate, like, let's say, materials for catalysis, people are interested in, like, the behavior of the distribution of the, for instance, of the catalytic particles on the ceramic support, like porcelain, oswald-Riepening, things like that. So people want to understand why materials fail, for instance, and so this is why they conduct heating, because how structures form. This is another application, how structures form upon heating. This is the recrystallization here of germanium. This is the growth of nanotubes in an environmental TM, so there is even some reaction gas introduced to facilitate the growth of nanoparticles. This is this crystallization of silicon that I already showed. This is the reduction and the structure formation of a fuel cell anode. And here on the right-hand side, you will see one example of the growth of graphene on the surface. Let me just start those videos. So this is the dielectric at high temperature, so in high vacuum, 350 degrees C. And in this particular case, one of our PhD students was interested in, like, let's say, the formation of those structures and the retraction of all those struts in between. So, because commonly, if you conduct such an experiment ex situ, you would just investigate your starting or your original state, and after a certain period of time, you would look at the sample again, isn't it? And you would end up just probably with a model. And here, I mean, the question was about whether the material, the gold, is transported via surface diffusion, via interface diffusion, or I mean, there are many ways how to redistribute the metal, and this all depends, I mean, on what's going on during this relative process, isn't it? This is just the recrystallization here in high vacuum at different temperatures of this uppermost tip. So this is liquid here, now it crystallizes, and in principle that occurs atomic layer by atomic layer if you look carefully. So I mean, structure formation, it's not that there's just something going on the bulk and it recrystallizes, but commonly it nucleates at some point, and then atomic layer by atomic layer the material crystallizes. So this is, for instance, a transformation of an amorphous phase to crystalline phase. At the right-hand side, this is, as I mentioned, the growth of carbon nanotubes. There are catalytically active particles. You introduce the gas, reaction gas, to observe that. This is another experiment in high vacuum here. This is this recrystallization of silicon. You see this bent contours and some diffraction contrast. So this is the aluminum film that Balaji may utilize for this Allyl process. And this is already this crystallized silicon layer. In this particular case, the question came up how the aluminum from this lower layer is transported into the upper layer. Just, let's say, through this diffusion barrier that was deposited as well. And it turned out that in some areas, which you hardly see here, that this diffusion barrier layer just breaks, and you have such a very rapid push-up of the silicon because there is some stress involved. Stress occurs, and that just causes the failure of this interlayer. This is the reduction of a nickel zirconium oxide anode of a fuel cell, where you see that the nickel, these are some nickel grains, in between there's some zirconium oxide grains. The nickel gets reduced here. This is done in hydrogen environment in a microscope at 240 degrees, and I mean, by that, people are able to follow the reduction, and if you cycle and if you operate a fuel cell, the question is always, whether those materials fail or not. Because if you, let's say, reduce in the first step and then you quench or you change the temperature of your fuel cell, you might even end up with a local oxidation and some redox cycling of your catalytically active material. And if that does not densify anymore and you have a composite material, inherent stresses might occur, and that might cause the flaking or the degradation of such a fuel cell anode.
So we can see the structural phase transition.
Pardon?
We can see the structural phase transition.
Yeah, in many effects, this is like the bright field here image. You see, this is the nickel. If you reduce nickel oxide to nickel, you gain volume because you lose all your oxygen, so the volume is smaller. This is why pores form in this reduced nickel oxide. But you have to think about what happens if you re-oxidize that.
Yes.
If you oxidize that in another step, for instance, it doesn't necessarily mean that all the pores, vanish. So just by this oxidation of your nickel, so meaning that some of these pores might even remain in the material. If pores remain, the volume of one grain is larger than before, and that might cause stresses, for instance. If, like, people are highly interested in failure of batteries or fuel cells, So you want to do such, let's say, cycling within the microscope. On the right-hand side, there's this growth of graphene. As you can see, there's layer by layer. You see some new layer of graphene forms on the surface. This is already multiple layers of carbon. This is a metal substrate here. This is done also by providing a certain reaction gas that provides carbon. The carbon dissolves in this metal here, and it just causes, upon supersaturation, it just causes the formation of a new layer of graphene on the surface. So this is what, let's say, what people want to do and what people still do. And I mean, this is another example on the atomic scale, just to show you, this is just some repetition about what people nowadays do and what they are able to do. I mean, this is just the observation of any kind of change of the material down on the atomic scale, isn't it? And I mean, there are, I would say, two advantages to do that with the parallel beam, you know, with the parallel beam illumination in HRTM mode or in conventional TM mode, because it's quite fast. You just record one image after the other, isn't it? In STEM mode, you always have to deal with slight drift, and you have to deal with like prolonged exposure times. This is like most of these examples which I show, and just the data is just recorded in conventional TM mode, right, in dark field mode or HRTM mode. But there are also examples like people, let's say, do STEM activities. This is another field. It's about environmental microscopy. Environmental means that we want to apply almost any kind of environment. That doesn't necessarily mean to apply like air or humid environment. In this former slide, you already saw that people, you know, introduce reaction gases here for the growth of graphene. You introduce hydrogen to reduce materials, and as long as, I would say, your vacuum system or your environmental microscope withstands your gas that you want to introduce or your liquid, you might be able to do that. And environment doesn't also necessarily mean to introduce a gas environment, because you could think about to work in a liquid or, you know, in a liquid environment. And how people realize that is, I mean, you have to separate, in the scanning electron microscope, for instance, you have to separate your chamber with at like increased like partial pressure of your gas from your electron column. Because I mean, we have our electron source. The electron source, like a field emission electron source, has to be operated under ultra-high vacuum conditions. And I mean, you cannot let any gas diffuse up to your electron source, isn't it? You want to keep your electron column free of that gas because of inelastic scattering, and elastical scattering in this gas environment is just a question about how you conduct those experiments. But nonetheless, 30 kilo electron-volt electrons are able to penetrate through, let's say, already a pretty thick layer of gas without any, like I would say, negligible or very low, you know, loss of resolution on your sample. So I mean, any inelastic and elastic scattering would cause a broadening of your beam in a scanning electron microscope, but up to a certain pressures, I would say. I mean, this is, you can see, in this particular case, it goes up to 3,000 Pascal. This is 30 millibar. I mean, 30 millibar, this is not a really high pressure compared to 1 bar atmosphere, isn't it? To 1 atmosphere. So, but people, they introduce like humidity, water vapor, they introduce just gases like hydrogen, oxygen, nitrogen. It depends on what you're interested in. What you have here in between is you have a so-called differential pumping apertures. So you have very small limiting apertures so that the gas from here to there or the diffusion of gas is just strongly limited by apertures. And you add additional pumping equipment, you add several of those apertures, and you add additional pumps to introduce a very steep drop of your pressure, okay, towards your electron current. So you need somehow many more pumps, meaning that in this particular case, you just flood the whole chamber. You might also introduce, let's say in a scanning electron microscope, you might also think about to introduce your gas on a very localized scale by using one of the gas injection systems, for instance. meaning you have this, like in focus ironing, you might have such gas injection systems right available, and then you can introduce humidity on a very localized scale by just introducing this needle, this injection needle, and to apply this gas environment just on your sample surface. So you can use some of these robot arms to equip those just with a fine tube to introduce gases on that scale. Unfortunately, doing it this way, you currently don't know the local pressure of the gas because it just gets dissolved. And so this is like why there are dedicated microscopes available. And even the EVO microscope that you saw in the live demonstration, the scanning electron microscope that was on the left-hand side, which we used for the live demos, this is not necessarily a high vacuum tool. This is already a so-called variable pressure microscope, and with this microscope you can introduce gases up to this pressure of 30 millibar. So that microscope already has this differential pumping aperture. For instance, if you're interested like in biological specimens, you would like to introduce certain humidity to the surface, then you can do it with this specific tool. So this is already a specialized microscope. So this is not just a high vacuum tool. Let me just show you very few examples of what people do in gas environment. I mean, this is a very simple one. This is heterogeneous nucleation of ice. This is ice due to water vapor at the microscope on a cold surface. And this is just how ice crystals form or ice layer forms on the surface. Okay? So pretty simple experiment. I must say I don't know exactly why they did it. But there are many other examples. This is the melting of salt at high temperature in the scanning electron microscope. Just another example. So this is a liquid phase here. This is crystalline, and just the liquid phase just covers now this liquid phase. This is upon cooling, recrystallization of the material just upon cooling. You see that the structure looks quite different.
So how it is possible cooling leads to the crystallization?
I mean, if you have
or any lower sample for crystallization?
no, I mean, yeah, but no, what you have here, if you have a purely liquid phase, this is what like working on metals, what they know, if you have a phase diagram, and if you have a liquid phase field, and you cool down, then nucleation will happen. So nucleation will happen and crystals will form if your crystalline phases stay at lower temperatures. Meaning that first you raise the temperature to melt the material, if you lower the temperature, you just follow the like phase diagram, and then how many nucleation occurs, and the crystallization happens. So this is quite common. There are two more, like I would say, examples which are more relevant, like in applications. This is a copper surface, and it's a very nice and clean sample, and I just got these from a colleague from Berlin, Mark Willinger. These are not published, but nonetheless, I would like to share those here. So this is just a copper surface in oxygen environment at slightly higher temperature. And so this is about the oxidation of a metal. And you will see that this is also does not happen all over the surface. So this is the copper oxide that forms on the surfaces. This is secondary electron imaging mode. And you see this nice growth, like let's say, of all those copper oxide crystallites. In this particular case, up to that state, it's not the whole surface is oxidized, isn't it? And the same material under, let's say, reaction conditions in a redox reaction. So in this particular case, hydrogen and oxygen are introduced. In the former case, it was only oxygen at these temperatures. And this is now like a, let's say, a chemical reaction because copper is it's catalytically active. And this is how such a catalytically active surface might behave. So this is, it's not that you have like certain like oxidation and reduction on the atomic scale. This is a pretty severe change of the morphology of a whole surface just during such a reaction. You see some areas which get oxidized, some areas which get reduced, and this is such an interplay between local oxidation and reaction and reduction of such a catalytically active surface on a larger scale. But how can we realize environmental TF? I mean, we have limited capability, so there's less space available. They do it in a pretty similar way. There might be either dedicated microscopes available, where you just introduce the gas environment on a very local scale, just right at your sample. So we insert our sample holder, we have our objective lens here, 2 pieces, and we have these differential pumping apertures all over the, just distributed in our electron column. We have additional pumps attached, and by that we are able to achieve certain pressures up to, let's say, 50 millibar. I mean, 50 millibar for catalytic reactions, 50 millibar is quite low. Catalytic reactions, they occur or they happen at pressures of 2 bar or so, or 3 bar. And there's quite a difference in your material. If you watch the material at 50 millibar or at 3 bar, there are a few examples already published. But nonetheless, if you want to observe, let's say, this growth of your nanotubes or so, this is what the people use for at Stanford to conduct such experiments. So this is a very, very specialized microscope. And you have 2 operation modes. You can either operate it in this environmental mode, or you can just pump it down to high vacuum conditions. So meaning that all of these environmental instruments you can also use under high vacuum. The other way, if you want to achieve far higher pressures, you might want to use such a MEMS-based chip. The advantage is of such a MEMS-based chip, so you introduce the gas just using you have very, very fine, very narrow tubes available, and you commonly combine 2 chips, 2 membranes, very thin membranes, silicon nitride membranes, and you confine your gas environment in between these 2 chips. So you have a sealing O-ring, you introduce your gas from the side, so just through your whole sample holder, and you just mount that together. The big advantage of such a dedicated microscope, although it just allows for very relatively low pressures, is that you can combine it with almost any other in situ holder. So you can easily do a straining experiment in hydrogen environment, for instance, or you can do a heating experiment with any type of heating holder, or you can bias your sample just by using a biasing holder. Here, you are always limited by the functionality of the chips. This is already a combination of such an environmental holder with a heater chip. So many people are interested to conduct experiments at high temperatures in a certain gas environment. So you have to think about how to realize that. This specific solution holder allows for both, and the pressures that are, you have to remember, or you have to imagine that those membranes are very small. So meaning even at 2 bar pressure, this is like a common range that you might achieve, even at 2 bar pressure, the force to these very thin membranes is so small, so low, that those wouldn't fail, So this is the reason why you can go to far higher pressures. And the distance, or the thickness of your gas, layer is commonly of the order of a few micrometers. So you have to penetrate with your electron beam through your confining membranes, through the gas environment, and that's finally through your sample. But nonetheless, at 200 or 300 kilo electron volts, you get quite decent atomic resolution data of that. This is one example that you already saw. This is the study on this, the lithium and the corrosion of the lithium, and I will not explain that in very much detail. I would just like to share just a second time this corrosion of lithium in wet environment. This is our metallic lithium here, and this is just this corrosion layer, which is highly open porous. And by such studies, we were able to understand somehow this reaction, or these reactions going on and causing this drastic degradation, like let's say, of batteries. This is just one example, one holder for liquid environment. So you have a very specialized tip of the sample holder. This is in a scanning electron microscope. You have like an inlet and outlet for your gas, for your liquid environment. And in this particular case, you also confine your liquid environment using 2 membranes, and you work in transmission mode here, even in a scanning electron microscope. The same holder or similar tip you may use In a transmission electron microscope, you have a dedicated holder for gel microscope in this particular case, and you just drive your solvent or your liquid, like water or so, just through this area where you just have these two membranes, and by that I mean you're able to observe or to watch any kind of structure formation, the growth of nanoparticles, or any kind of changes within this liquid environment. And as I mentioned already, you have to think about how the electron beam affects this liquid phase, for instance, because you can easily imagine that you ionize all those species because you have the interaction not only with your sample that you're interested in, but as well with your liquid environment, and by that you might change, for instance, the pH of water, because you introduce ions, the ion concentration is higher, by that the pH is different. Meaning, if the pH is different, if you want to observe any like growth or of particles, that might already cause some trouble. This is the growth of gold structures, like from a solution and some reaction educts, and you can see that there is somehow different growth modes of these dendritic structures in this particular case, and of this continuous growth, let's say, of more homogeneous nanoparticles. And I mean, if you just see the final state deposited from a solution just onto your, let's say, TM grid, you might not understand what's going on and why those different structures form, for instance. I must say that such measurements in the liquid environment are even more challenging than measurements in gas environment, because this interaction, I would say there are very few publications about this interaction with this liquid environment. This is quite challenging. This is a very specialized sample holder, let's say, to conduct electrical measurements in a transmission electron microscope. I mean, you can easily imagine that in a scanning electron microscope, it might be quite easy. You might even be able just to contact your structure using wires, wire bonding, using electron or any kind of lithography. And if you're interested in the electrical behavior of nanostructures, you might just disperse them onto the electrodes, and just due to statistics, there might just be some of the nanostructures lying in between the electrodes. In this particular case, this is a very specialized sample holder to conduct electrical measurements, two-pot measurements on a very localized scale in a transmission electron microscope. So in this particular case, the TM sample is mounted on the left-hand side, and on the right-hand side you just have like a metal tip installed, and you can manipulate your sample and move your sample and contact very, very locally. This is one example where we measured just the switching of TC and Q nanowires, so this is more an organic molecule, and by introducing currents up to certain field strength, you will see that the resistivity changes. The question was, people want to make use of those switching materials to realize circuits on a localized scale, and so we approached with this metal tip here on the right hand side, the other way we approached this metal tip with our sample by just moving our sample, and just by contacting individual nanowires, we were able to demonstrate this hysteresis, so the switching behavior depending on the applied current. So you can do that on the localized scale. You can directly contact individual nanostructures. This is what you can do in a scanning electron microscope as well, just by using such nanomanipulators, for instance. And I mean, this is like only one example why people want to contact materials. I mean, if you have like a nano device that you want to test, or a fuel cell or whatever, any kind of battery, people are interested in the electrical behavior. So there are many questions why people do that. There's a very nice example. I couldn't find it. I couldn't find the movie yesterday. There's a very nice example. People might be interested in electromigration. So whenever you run a current through a device, like metal species might migrate, and this causes the failure of devices or like metal contacts after a certain period of time. And there are people who even just prepare TM samples where, let's say, your metal channel or your metal contact is confined, and they run a current and they watch this electromigration in real time to see where the failure occurs. And I mean, this is quite demanding, because I mean, you want to keep all the material intact, just to have your metal channel or your metal contacts embedded in your material while you are penetrating with the electron beam through the structure. I mean, this is why you use the focused ion beam point. I mean, we already saw that for many of these in situ studies, you make use of a focused ion beam to generate the samples. And it always depends on the material that you work on in the study that you want to conduct. In principle, there are many ways. And I would like just to encourage you to think about, so if you have any idea and like I say, any question to that, then I mean, we are open for discussion. But Balaji knows people in that field, we know people in that field, and I mean, it's just up to you, I would say, to initiate those studies. And with that, I would like to finish for today, so we are right in time for our coffee break today. And yeah, with that, this was the last slide, I would say, of our course. With that, I would like to thank you for your attention during the last 2 weeks.
That was the concrete call that I just received. But I take this opportunity in the meantime to introduce my colleagues who are sitting here. And after that, I would also want you to introduce. And as soon as the rector comes, we'll stop this business of introducing each other. We'll get on with the important task, because he may not stay here for long. This is my feeling. And also, I mean, once the rector has come and has done his job, anybody who is urgent, has trained, his request will be entertained. No problem about that. So, good. So, okay. So, Professor Vijay Kumar Kumar, he is the chairperson of my center, where I come from, Special Center for Nanoscience, and Dr. Pratima Solanki. So, we are all colleagues. And in fact, Special Center for Nanoscience was started new, as you might not be knowing, but so we are the more or less the first faculty members of that center. Good. So, I mean, Nanoscience Center and JNU in general has given us, or at least me, this platform to be able to organize a course like this, and so we have a lot of things to say about each other. But I would say that I have introduced them, and let us, sorry, and I also forgot about Dr. Tulika Prasad. She is also associated with our center, and but she is also associated with ARF. So, as you know, our course was actually is also heavily indebted to ARF, because we used their machines, we visited there, all our demonstrations were done there. Research persons from ARF, Dr. Ruchita Pal and Mr. Manu, who I think has not come, but they have been instrumental in having this as a success, because it was not just lectures, but it was also demonstrations, and I personally feel that it is the demonstrations which really are more difficult to conduct and organize than lectures, and many times they have much more impact than the lectures. So I therefore have special value for their role. Okay. With that, maybe we start from one side. So maybe Shweta, you can introduce yourself.
Hello, I am Shweta from Rourkela, and I am working on magnetoelectric materials. Basically in biphasic materials, because in our views and from literature also, biphasic or multiphase system shows large magnetoelectric coupling. So from that point of view, we are interested in biphasic systems, lanthanum nickel magnet.
My name is Prof, and I am doing PhD in IUC, Inter University Accelerator Center, where I am currently working for the India-based mobilization.
Myself, particularly Prasad, doing research on structural ceramics. So I am thankful to this course. I got some software details here. Thanks to them for us.
I'm Archit Tomar. I'm working as an assistant professor in Noida International University. And thank you so much. This course is really, really informative for me. Thank you.
Mandeep from NIT Nagpur, working on advanced nanostructures for gas sensing applications.
I am Pawan Kumar from Mechanical Department at NIT Chapter. I am
pursuing PhD undergraduate with Dr. Balaji Virajwar, Special Science and Neuroscience. I am currently working on beta-hydroxy ion nanostructures.
Hi all of you, my name is Siegen. I am a research scholar at IIT Delhi and I am working in high entropy alloys, characterization of high entropy alloys.
Hi everyone, I am Mohammed Ansari. I am a research scholar in IIT Delhi and I am working on magnesium atrium alloy, deformation, mainly deformation behavior of the magnesium atrium alloy. Thank you.
Hi, this is Shankar. I'm research scholar at IIT Roorkee. I am currently doing research on the electrochromic device, which is actually main portion is its fabrication and its application.
Myself Anita Manhas from Shimla, pursuing my PhD from HQ Shimla, and my area of research work is to synthesize ferrites, basically soft nanohexaferites for nano antenna application in S-band of electromagnetic regions.
Hello everyone, I am Ajit Kumar Devari. I am pursuing a PhD from IIT Gandhinagar. I am working on the Institute Deformation of Silicon.
Myself Kunal, I am a PhD student at IIT Gandhinagar and I am working on the interface structure and its dynamics.
Hello everyone, myself Mishra. I am from IUSC and I am scientist there, and we are installing a new TM facility.
Hello everyone, my name is Lalit Singh, pursuing PhD from Department of Physics, IIT Delhi. I am working on CVD growth of molybdenum disulfide and effect of radiation on its properties.
Hello everyone, myself Marsha Gupta and doing PhD from IUC New Delhi and working on semiconductor to metal transition.
Hello everyone, I am Farida from NIT Manipur and research work is synthesis of hydrogen nanoparticles for magnetic and optical nanoparticles for hyperthermal applications.
Hello, myself Supriya Kudale. I am from University of Maharashtra and my work is on nanotubes for biomedical applications. Hello, myself Andhariti Palidapatrai from Aurangabad University, Maharashtra. Now just joining for PhD work under the guidance of K.M. Dharuka.
Hello, I am Manish. I am from Maharashtra and my topic is aerosol. I have it for water purification application.
Hello everyone, myself Devyada and I am currently pursuing my masters from Delhi University.
Hello everyone, myself Sadra Yadav and pursuing masters from Delhi University.
Good afternoon to all. My name is Sandeep Kumar. I belong to district Mandi, Himachal Pradesh, and I am doing my PhD from Anna University.
Good afternoon and all. I am Satyamurthy. I am from Tamil Nadu Agriculture University. I am working as an assistant professor. Actually, my field of expertise is life science. So to me, it seems to be a little bit odd because of this advanced technology. But still, I am finding the way to how to use this technology in our field. Thank you.
Good afternoon all. I am PS Manoj Anjana from CSR NML. I am currently working on Inconel 718 alloy and its creep fatigue interaction also.
Good afternoon everyone. My name is Mudassir Akhtar from Jamshedpur. I am a research scholar in CSIR NML Jamshedpur. I am working on creep fatigue interaction of Odimate 720 Li super base nickel base super alloy. Thank you.
Good morning everyone. I am Sudipta. I am from Delhi University. I am working on investigation of bioactive glass for the biomedical applications.
Yeah, good afternoon everyone. Myself Aman Arora. I am working as scientist at SSPL DRDO Delhi.
Hello everyone, myself Pramod Gupta. I am working on nanobiosensors and currently I am evaluating my work at SCNS under Dr. Prof.
Hello all, my name is Rajendra Tiwari and I am doing PhD under the supervision of Dr. Balaji Virajwar at SCNS, JNU.
Hi everyone, I am Uditma from Delhi University. I am working on magnetic nanoparticles.
Hello everyone, myself Yashika Sharma. I am a PhD student and I am working under the supervision of Professor Siegen, Department of Physics and Astrophysics, University of Delhi. My research work
completed my MSc in Physics 2007 and seeking admission for atmospheric science or remote sensing in JS Apply.
Hello everyone, myself Arun Kumar. I am working as a technical officer in the university in UC.
Hi, my name is Subhavna. I come from School of Biotechnology and I work on Raman spectroscopy based bioimaging.
Hello everyone, I am Dispansin from the Govind Singh University. Yesterday I have defended my PhD viva.
School of Environmental Science JNU. Presently, I am instrument in charge of EPR, Electron Paramagnetic Resonance Spectroscopy and Flow Cytometer at AIML.
Good afternoon to all of you. I am Dr. Anu Singh. I am working as a UGC postdoctoral fellow and my working area is development of electrochemical biosensors for cancer diagnostics. So we are developing novel nanomaterials, so this course is going to help me in characterization of those novel nanomaterials.
Hello everyone, myself Dr. JNU. I am working in Advanced Information Research Facility as a technical assistant there, and I am in charge of ion beaming system and rectangular process microscope.
Hello everyone, I am Sushil Kumar from Gautam Buddha University. My area of research is semiconductor devices.
Yeah, I mean, many are from Delhi University. He was long time working with Delhi University also. So now let me know whose trains are pending. I think yours is 4 o'clock. So I would say, I mean, it would be very unfortunate. You will not go with good memories if your train misses. So I will at least give it to you, and so long as you can hold here, you hold. Please, you I mean, just give it.
Clicking the photos.
So please, okay, so Professor Satish Gatkoti is a professor in School of Environmental Sciences of Jawaharlal Nehru University, and he is now also the rector of the university. So he has many publications and he is a well-renowned scientist in environmental sciences. So I would not like to take it too long. We have already introduced each other, and I will tell briefly about Professor Benjamin, and then we'll go through some of the, just to give, so that I would like to keep it this way, that both Professor Benjamin and myself will sort of together tell you briefly to get an idea as to how this course went, and then maybe we would, we would request you to say a few words, and then we want to thank, because many people have contributed to this, and we want to spend a few slides on that, and that I think this is how broadly we will conclude it. But if you are urgent, please let us know, and we will accordingly adapt to that.
I can be here safe for some time.
Okay, okay, so, okay. Good, so
I think maybe you can also get up and we will, maybe you begin. That's because this is something from your side. So I was supposed, however, to tell something about Professor Benjamin. So he did his diploma and PhD from Karlsruhe University of Technology in Germany. And then subsequently he joined as postdoc in the group of Professor Spieker in Erlangen University. And then subsequently he also became a staff scientist, a permanent position, and assistant to Professor Spieker. That was also the period wherein I had overlap with his tenure because we were simultaneously working with Professor Spieker in his group of electron microscopy. And eventually he went to Stanford University for 2 years. And since October 2007, he is now a full professor in the chair of microanalytic at University of Siegen, also in Germany. To tell about Professor Benjamin, he's very hands-on sort of person, and we have immensely profited from his expertise. And I mean, I think they have all enjoyed it, and he has also apparently enjoyed interacting with the participants. So with this, I think we will go ahead with giving you a glimpse of how this course went along. So Benjamin, please.
So now it's my turn. Okay. I mean, first of all, I would like to thank you for all your your attention during the last 9 to 10 days. I mean, I know that it was quite a very intense job or work for you as well as for us. So we went to bed firstly at 1 o'clock or 2 o'clock in the morning almost every day. For me it was new since the first time in Asia, the first time in India, and I must say I have enjoyed it very much. So we will definitely come back at a later point, probably not during the next year because we will have to do a lot of work to set up our new group. This is a very few slides just about what we have covered, you know, what you have learned about during the last 10 days. And as you realized that we somehow adapted our schedule from the very early beginning, so it was a little bit different to what we wanted to do, but nonetheless, on the one hand side, to adapt to your needs somehow. So, I mean, this is exactly or almost the same slide that I showed the very first day, isn't it? So with many examples about material science, materials research using electrons and the focus ion beam. And now, after 10 days, there should be some of these pictures that you already saw that, you know, you could, I would say, you should get an idea about what you might see here after these 10 days, isn't it? So there's some imaging, some tomography, some spectroscopy, and this is all the topics that we have covered, I would say. And I mean, there are two people like Balaji here who has contributed a lot to realize that workshop. And first of all, before you do anything, I would like to thank you for the invitation. Like we discussed that almost 1 year ago or so, when I still was at Stanford. And for me, it was right clear from the beginning that we would do that. I know that electron microscopy is, well, a little bit not new, but it's strongly developing and raising in your country. And I think there is a lot of demands from your side. But I think there are many opportunities to contribute to excellent materials research, and I mean this is what electron microscopy is used for. It's not only about methods development. We want to do a lot of material science. We want to contribute to develop new materials, probably or prospectively to save energy, you know, for catalysis, for any kind of materials research. And so let's come to the first, just to the first slide to conclude about what we have done during that 2 weeks. So this is our schedule. This is the final version of the schedule that we will also use probably prospectively for the next workshop. So we covered all these topics. We had 2 sessions of lectures every morning except the Sunday. Sunday was off. I enjoyed that also very much to have 1 day off. I suppose it was the same with you. Because it was quite an intense time. As you can see, almost every afternoon was covered up to 5 o'clock or 6 o'clock, depending on your live demonstrations at the microscope. We started in the afternoon with sample preparation the first day, as we figured out that this would be some valuable information for you. We had some general discussions, all these demonstrations. So in principle, we covered 30 hours of lectures during the mornings and few afternoon sessions. I mean, 30 full hours, so this is not only 45 minutes. I mean, this is quite a lot. We covered almost 24 hours just for the real demos, plus all our preparation. we had spent before, because I already arrived on Sunday, because we had no time to prepare that very well, I must say. So I just received this SEM sample 10 days ago or so from the KIT in Karlsruhe that was prepared for us. We had like roughly 15 hours of tutorials and demos plus like numerous discussions about like specific projects. So I hope that almost every question was somehow addressed. And I mean, we covered just, I would say, a very broad range of electron microscopy topics in the scanning electron microscope as well as in the transmission electron microscope, just from this, here it's like the diffraction, electron diffraction contrast imaging, the atomic resolution techniques, capabilities, the spectroscopic techniques, tomography, and so on. So I mean, this is pretty a broad overview, and I mean, in principle, this is also what we teach our students, but for our students, we have like 3 courses of that length available, but it's just distributed like over 1 year or so. So this makes things a little bit, I would say, easier for us to teach, because we have 1 week of preparation just for 1.5 hours session, so the quality might even be better. But nonetheless, I hope that you enjoyed it and that like this content has covered like what you expected before you came here. So whenever something is missing, just let us know. I mean, you submitted your like feedback forms, and I hope that we're going to get some criticism with which we can even like improve our workshop for the next time. So with this, probably you would like to proceed, or?
Okay, so this is just a snapshot of Professor Benjamin delivering his lectures. So that was for the morning periods. But I must say that, I mean, apart from lectures, we also had a lot of demonstrations, and that actually kept us, and probably also the participants, on their toes, as well as kept them interesting. So this is SEM demonstration being conducted by Professor Benjamin, and with the help of course, Dr. Ruchita Pal. And this worked out very flawlessly, but it was not really, we were ourselves not very sure. I mean, with lectures, we could be sure that they will perform well or they will go well, but with the demos, it is always a suspense, and it worked out well, and we are very fortunate about that. Next slide. Okay, so these are some typical results. He said that you have analyzed that superconductor sample, niobium titanium also, and its structure, so you are seeing the different morphology and EDX mapping and all that. So just to summarize. Okay, and then this is the next demonstration. So we had, I would say, 2 real practical demonstrations. One was on scanning electron microscopy and the other was on transmission electron microscope, both at AIRF. And this is where we are now thinking about our, this is a photo of the demo on the transmission electron microscope, and the results we will see in the next slide. So, so there we have, pardon, it's not there? Okay. So we have analyzed, I mean, we had chosen aluminum sample, so that was our common packaging foil, and we studied its microstructure. So you have the zone axis diffraction pattern, and then we have the bright field image, we tilt it into 2 beam conditions, and then we get, this is the dark field image. So we find out the grain size, we can see some precipitates, grain boundaries, dislocations, etc. And then Professor Benjamin, who has extremely, for him, doing scanning transmission electron microscopy is like, even if you wake him up in the night and ask him to get an image, he will give you in 5 minutes. This is a scanning transmission electron microscopy image. You can see again the grains, and then you can see the chemical contrast like that of the backscattered electrons in the SEM. And this is the corresponding same STEM image, but at smaller camera length, so that you get the Z contrast and all that. So here there is still some diffraction contrast. You see the grains here; those go away, and only the pure chemical contrast remains, and so on. So okay, thank you. So yeah, good. So actually, we must also acknowledge that I mean, it was that you saw that he had to prepare the lectures almost, I mean, late in the night to face you every morning, isn't it? Now that was also done. Yes. So he was also assisted by his postdoc, Dr. Julian Müller. By the I also know him from my days there. He's an excellent person. So you may not have seen him working here, but he was in the background. He was also assisting Professor Benjamin in getting the slides. They had to work out. I mean, they would call on the phones. This needs to be done that way. So we want to acknowledge them also. Next slide, please. And it's both Professor Benjamin as well as myself. We have learned all our microscopy from, let's say, these three professors. They are already fairly senior. Professor Hesse has already retired, and Professor Oliver Eipel was my PhD supervisor at University of Tübingen. And we have forgotten to put in the photograph of supervisor of Professor Butz, Professor Gersten. Yeah, so but we acknowledge her, and we have learned all that what we have transmitted to you from these big persons. So we acknowledge them, and Professor Spieker's photo, he's the one from University of Erlangen, University of Tübingen, and that's Max Planck Institute of Microstructure Physics in Halle. Okay. So this is how it began. So we are very, let me tell you that there were 230 applicants, and it was hard time to really sort out, and it is really a very tedious task. You imagine an Excel sheet with 230, and then you have to find out. So it was quite a bit of time consuming task for me to shortlist them, and I couldn't, I mean, I had to be also objective. So I have tried to be little bit partial towards those who had studied mathematics, material science, physics, and like that. And I must admit that I have tried to be little hesitant in keeping the biologists, thinking that it might be that it might involve too much of mathematics, etc. So it was with that intention, but nonetheless many biologists specially requested that they want it, and then I have entertained them. So many biologists have also made it into it, and finally we realized that it was not such a bad thing even for them, because Professor Benjamin then adapted his lectures little bit to ensure that they also get significant benefit from it. So this was one of the first 2 days that we made a photo. We, however, want to make a similar photo right after our session quickly. We hope that we make it. So we will try to get the photo with the rector as well. Okay, so good. And I must also say that participants have come from all over India, from Manipur, from Tamil Nadu, and from Gujarat. So we have received overwhelming response. I thank you very much. And not only that, the response was maintained. It was not that first day everybody came and then slowly the interest disappeared. That didn't happen, and I think that has largely to do with the hands-on approach that Professor Benjamin adapts, and also probably because of the practical demonstrations that we had. I think that kept us busy, but also kept us interested in the whole thing. Here I acknowledge Special Center for Nanoscience and JNU and my faculty colleagues that this gives me a platform to be able to conduct such a course and let's say learn more or proceed in expanding the knowledge and building upon it. And these are my PhD students, Rohtash Kumar, Inderjit Singh, Rajendra Tiwari, and Rupesh. So they have also very significantly contributed to conducting these exercises. We have been giving you such kind of printouts almost every morning, and so they had to run after getting it and so on. So there's a lot of work that they have done even in the shortlisting. So in the last days, I relegated all these tasks to Rajendra Tiwari, Inderjit Singh, and so on, and they have done a magnificent job, right from printing posters to banners and so on. So they are, so let's go to the next slide. Yeah, and the ARF team, so right from the director who kindly permitted us to utilize the facilities of ARF, and the deputy director, Professor Vibha Tandon, and of course the two resource persons, Dr. Ruchita Pal, she was the one who was assisting us in ACM demonstration, and Mr. Manu, who helped us with the TM. So as I said, I have, and indeed we were almost, the TM was almost, had in fact broken down after the first session. But the dual service engineer, he was kind enough to come, he repaired the chiller. So this happened on Friday, and on Saturday, Sunday, I think they came on Sunday, isn't it? They came on Sunday, they repaired the chiller, and we got the news on Monday morning that things are still okay. So our Monday afternoon TM session could therefore be conducted. So otherwise we were talking with IUAC people if they could somehow help us and all that. I am going to come to IUAC. They have also played a major role, and 4-5 of their participants are in the audience, and they have set up an excellent sample preparation facility. They are also setting up a very nice advanced transmission electron microscope. So and we have sort of been very benefited from their collaboration and participation. Good. So now, by the way, these photographs and all that I have put, it was done in a haphazard manner. So some have come, some have not been come here. That was because it was being done while this was also being simultaneously organized. So now no more photographs. Now I have switched to just the text. So I have acknowledged JNU and SNS abundantly. I also want to acknowledge this building, Jawaharlal Nehru Institute of Advanced Studies, and this provided us excellent atmosphere. We were in a very peaceful atmosphere here, and we enjoyed our lectures as well as the demonstration, food, and all that. And for the we thank the corresponding contractor. Rotash was responsible for looking after that. And here I mentioned about Inter-University Accelerator Center, and especially we want to mention Dr. Kabiraj. He has been wholeheartedly supporting us in helping. And in fact, we had, so I said that there were 2 demonstrations, SEM and TM, but for sample preparation, we have more or less asked the participants to visit IUAC and have a look at that, because that's very elaborate, and only in the theory sort of lecture we explain how it works and all that. By the way, they have also done, and Mr. Ambuj Mishra is among us, and he was instrumental in explaining the sample preparation facility to the participants who were interested. Also, here we have forgotten to write down about guest house, but at least 16-17 of the participants had been accommodated in the Aravali and Gomati guest house, and they have been kind enough to provide this facility. That's how I think majority of the participants coming from out of the NCR region could be accommodated, and they benefited from it, and we are thankful about it. So next slide. That's all. Okay, so with this I think I have finished, and I would now request the rector to say a few words.
So thank you very much. So he just talked about out of 230 applicants, only 60 he could just screen for this program. So this is always the case with Jawaharlal Nehru University. So out of the total student applicant, they apply less than 2%, we just select for admission. So this is the case for almost for whatever courses we organize in HRDC, teachers, participants, the same thing is the case. Sometime after say 6 months, 1 year, 1.5 years, we just call for them for refresher courses or orientation courses. So this number here talks about the successful, this microscopy course here. Under the GAN program, basically what happens, so this, to me, it is very unique program of Government of India. Here, based on the gaps we have throughout the country in terms of the expertise, so we identify those gaps. Based on that, we identify experts abroad. We contact them. Our host faculty will develop a proposal, it is submitted, and then they screen it is sent to experts finally endorse it, and it is approved. So this program today is the result of all sort of the process, and you are here. We are thankful to our expert who has kindly spared the time to come here and train our people. So now the thing is, this is not the end of the day. So you got some expertise during last 2 weeks you stay here, so you have to take it forward. So whatever gaps you have identified, whatever you could learn, from there you have to start, and you have to contribute for the science of this country, right? So why I am saying this, say like JNU, we just proudly say that we are #1 in the country. So that is proved through our NAC accreditation, through NRF ranking, through Visitors Award that is given to JNU, by Government of India. JNU is #1 in country, but we have not reached to the 100 club, that is the global club. Right? Forget about all other universities that are part of this country. So it is the responsibility of all of us, right, to take this country to that 100 club, right? So we should start there. The second thing is, so you are the part of this program. This Gian cycle is continuous. Now this coming month, again they are going to have advertisement. So you just propose some courses that you feel that are going to be unique and they should be conducted, whether it is in your university or by JNU. You just write down, you make notes, then identify the gap and write down people, the faculty here, right? And they will develop the proposals and again you can join this. So I wish all success to you. Thank you very much.
So I will now proceed with the certificate distribution. And I came to know that some of the participants are pressed by time. So I will give them first. So I will read out the name Matipalli Prasad. So anybody else who is pressed by time, please tell your name.
PS Manoranjan
JNU.
Simply you come forward.
You come close. Aman Arora. Sarla.
Priti Rao and Aman Arora.
Sarla and Divya.
Sarla.
Manoranjan JNU.
Oh, she's coming?
Yes.
Oh, I got it.
Manoranjan JNU. You said Microscopy, correct? Yes. Yes. So I hope the urgent people are finished. You are from Delhi University only. Let us be Julian. They have trained Okay, so now we are we can do it. So now you. So Lakshmi. Deepa Oberoi, Pravada, Deepa Oberoi, from the same institute, so Pravadas, Anita Kumari, Ambuj Mishra, Akash Kumar Singh, Manu, Jaspal Singh, Jitendra Singh, Khedkar Mangesh, Neelam Desh, Nuruddin Ansari, Patade Supriya, Nuruddin Ansari, Patade Supriya, Pramod Kumar, staff. Soumya, Saurabh Kumar Sharma, Smruti, Pawan Kumar, Pawan Kumar, Ranjit Kumar Devuri,
Ranjit Kumar, Sandeep Kumar,
Sandeep.
Satya Murthy, Shivam Saxena, Danshu Kumar,
Shivam Kumar is coming, isn't it? Yeah. Sorry, Shivam Saxena. Shivam Saxena. Sudhanshu Kumar. Harsh Kumar. Bandi Suresh. Neetu Singh. Bandi Suresh. Dipali Andhare. Dipali Andhare. Amarnath Yadav. Aditya Singh. Dr. Ruchita Pal. Himanshi Gupta. Shweta Kumari. Inderjit Singh. Rohtash Kumar is busy repairing an instrument. Sudipta. Sushil Kumar. Jai Shankar. Jai Shankar. Rajendra Prasad. Deepika Sharma. Amodini Mishra. Okay, yeah. Benjamin, you have to join.
It will be a memory whenever I see the photo, I'll remember your face too.
Yeah, but not everybody should make such a request. Thank you. So, Archit Tomar, then Smita Sundaram, Smita Sundaram, Vicky Nandal, Vanita, Muditma, Ashwani Kumar,
coordinator or the proposer is Dr. Balaji Viradar from Nanoscience.
Thank you, sir, very much. And, so with that, I think. So now we would, yeah, what was
Group photo.
Yes, so we head towards group photo, and with that, yeah, with that we will more or less conclude. So there's one little bit unpleasant, not so unpleasant, but you see, due to some reasons, that payment has not worked out for some of the people. They are all either from JNU or from IIT because they were on the spot registration. So the certificate has been given to you, but it will be better if just for the sake of, let us say, let's say ease of knowing things, it will be better if you give back the certificate and take it. The payment has been, it's optional